Jomok is back.
Yes.
Okay, hello.
Hello. Hyvää päivää.
Hyvää päivää. So where did you go and finish?
Well, I was going to Finland when I was 20 about, and for a few years, and then I studied Finnish for 2 years at the university in France.
Oh, 2 years.
Yeah. Yeah, yes. At that time I could speak a bit, but it was more than 50 years ago.
In Finnish, do you have accent like goes up and down?
Oh, tones, you mean? No.
Yeah,
It's rather
tones.
flat.
Very flat.
It's rather flat. Accent is on the first syllable of a word.
Yeah, it's quite a difficult language to learn.
And is it Kaisa? Is it Kaisa? Is it?
It is Kaisa.
Okay, AI, Kaisa.
Yeah.
Okay.
There is
Pronunciation is very easy in
there is
Finnish.
no sh, no real S. So the S is slightly, depending on the people who is speaking, it may be slightly tint. Well, it has a slight color of a sh, but
Yes. Okay.
so some people would put more on the sh, and some people just exactly on the s.
You have some little language in Bangla, the S, the sh is. It's not like the French S, which siffle. So after that, we have Chandi, we have Lee, and we have Ratiview. Chandi, I don't know whether it's Chandi or Chamde, or maybe Chamde.
Radziwill, you not use the Polish way to write the L.
Yes.
Yeah, I noticed. I just noticed it myself. Yeah. I usually use it, but for some reason when I made the slides, I haven't. I don't know why.
Well, if you want people to recognize him, it's better to call him Radziwill than to call him Radziwill. Because otherwise people are going to ask you, who is that guy?
Okay, better now.
Ah, yes. The L has appeared.
Great.
And was in the station of Poznan. I mean, I was looking for the station of Poznan, and I couldn't find it. And I kept asking people, can you show me where is Poznan Glony? And they told me, we don't know where is Poznan Glony. I mean, no way. And then after half an hour, it was getting close to the time when I should take the train, you know. So I was getting a bit anxious. And then people looked at what was written. And it was written Poznan Wuni. Because the L bar changes the G completely.
Oh, yeah.
Uh,
Nowadays, it's really a word.
yes.
But the shift from L to W is something we know in French. The plural of words in al are in O.
Yes, yes, yes. But yes, 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 yes.
Maybe I introduce, I just give it to John Mark for this talk.
Okay.
Welcome everyone to the second session of this final day of the conference. So I request Professor John Mark to chair this talk because he was the actual chair of our talk earlier. Thank you, John Mark, for agreeing. Over to you.
Okay. Thank you very much. So I have the pleasure to let Kaisa Matomaki from Turun Oslo to present a talk on moments of Dirichlet L functions. Please, Kaisa.
Oh, it's like 2 minutes to fund. Do you want?
Yeah, we still have 2
Okay.
minutes.
I guess we can wait for the 2 minutes if there are other people.
Yeah, I think yes, yes.
26.
From my point of view in Montreal, it's nice to wait because it's kind of early.
Yeah, oh yeah, it's really early for
The
us.
sun is, I'm going to see the sun go up.
In Montreal, it is 7.
Yeah, it is 7.
Yeah.
But we just changed the time, you know, we changed the time 2 weeks in North America too. So in the morning, it's still dark. We changed the time 2 weeks before everybody.
Yeah, but in Vancouver or Seattle, on the West Coast, it's even late.
Oh yeah. Yeah, this is very early.
Yeah, we are very happy to have so much daylight these days compared to the December when we didn't have snow yet and 6 hours or 5 hours of daylight. It was terrible, but now very nice.
And now
with
the
sunny
days are
days.
changing so fast. Yeah, every day you see a big difference. Huh? The slope is very big. Yeah, especially for you. You're northern than us, so it gets very short.
Yeah, I was in the Faroe Island for Christmas, and we had the sunlight between 11 in the morning till 3 in the afternoon. So it was difficult.
Here it's like 9:30 to 3 p.m. or something like that.
Wow.
Then it's the darkest time of the year. But in the summer, it's always light.
Yes. Then you can get lost in mountain.
So, okay, maybe we
Okay, you
go
start.
into real business. And so, Kaisa Matomaki will speak about moments of Dirichlet L function. So please.
Okay. Thanks a lot. Thanks to the organizers for inviting me. It's a great pleasure to speak here, and thanks for rescheduling my talk for today. So I will talk about moments of Dirichlet L functions, and everything will be joint work with Morapanchandi, Xianan Li, and Maxime Radziwill. Okay, I will start with the most simple case of L function, that is the Riemann zeta function, which is probably very familiar to you, but I will start with the basics. So we define the zeta s by the Dirichlet series of n to minus s for real part of s greater than 1. That's when the series converges. And then we define it through analytic continuation to the rest of the complex plane. And this is the simplest possible L function. And for this, the moment question is looking at integrating over t. The critical line for the zeta function is the real part of s equal to half. So we are integrating over the critical line and taking the 2kth moment of the zeta function. And this is the moment question. One wants to get an asymptotic formula for this, or at least an upper bound. And we know quite well what we expect. We expect that the 2kth moment of the zeta function is of size t times log t to k squared, which means that the sort of average size of zeta is a bit larger than 1. But what is expected is not what is known. We know asymptotics only for k equal to 1, that is the second moment by Hardy and Littlewood, and for k equal to 2 by Ingham. And asymptotics are not known for any other value of k. And it's quite an important question to get such asymptotics. Understanding the moments of zeta has applications, for instance, to studying the behavior of divisor functions and to prime numbers, as well as to the zeros of the zeta function. For instance, getting higher moments would immediately have implications towards primes in short intervals and so on. Okay, so let me first, before going to the other functions, sketch an upper bound argument for the zeta function. So for the L functions, there is an important parameter called the analytic conductor, which measures the complexity of the L function. And in case of the zeta function, this zeta of half plus it, this analytic conductor is about of size, the absolute value of t. And morally, the approximate functional equation allows us to approximate zeta at half plus it by a corresponding Dirichlet series, which has length square root of the conductor. So that's t to half, essentially. And to be precise, there should be another term with Dirichlet series n to minus half plus it, but let's not care about that. And also there should be some weights, but this is morally the story is that we get approximation by this Dirichlet series. And if instead of the moments of zeta, we look at moments of this Dirichlet series that approximate this zeta, we can use the mean value theorem for Dirichlet polynomials. So if we look at 2kth moment of this Dirichlet series, this is the second moment, of course, of the kth moment of it. And for that, we can apply the mean value theorem for Dirichlet polynomials, which tells us that the mean square of a Dirichlet polynomial is at most the length of the integral, which is t, plus the length of the Dirichlet polynomial whose square we are looking at, and in this case it's of length t to k over 2, times the mean square of the coefficients. And now if we evaluate the mean square of the coefficients here, it's of size log t to k over k squared. And one can make this argument rigorous and obtain an upper bound for the 2kth moment of the zeta, which is of size t times log t to k squared, when k is equal to 1 or 2. For larger values of k, this is off by factors of t, which is bad, but for k equal to 1 or 2, the first term is the dominant one here. And that's why we get the correct order of magnitude upper bound for the 2kth moment. There is a bit of technicalities, in particular related to the fact that the approximating Dirichlet series, the length depends on t, so we can't just have here capital T, or there is some technicalities about that, but that's not too difficult to make this rigorous and get an upper bound. But we wanted to get asymptotics, and it takes more effort to do it. But in any case, I don't think it's surprising that asymptotics are only known for k equal to 1 or 2, given this heuristics here, which is sort of the most obvious attack towards these moments. Okay, so after describing what happens for the zeta function, let me turn into Dirichlet L functions. So let chi mod q be a primitive Dirichlet character, and we defined L as chi by the Dirichlet series chi n over n to s for real part of s greater than 1. It has an Euler product, and for other s, we define it by analytic continuation. And here one can ask moment questions in two different aspects. There are two parameters, s and chi. We can ask about q aspect, which is the aspect of the conductor, and in T aspect, which is sort of the on the critical line. Here the S is half plus IT. And now the analytic conductor, what measures the complexity of the L function is Q times T, essentially. And in this talk, I will concentrate on the Q aspect, and I will almost fix S equal to half. I will later explain what I mean by almost fixing it. But let me mention at this point that Balasubramanian has work on moments also. And for instance, he has studied the moments of Dirichlet L functions at half plus IT with the average over chi. But I don't go into that more. I will move on to talking about moments at the critical point L half chi. And about that, we know by work of sound that we have an asymptotic formula for the fourth moment. The second moment was known earlier, but sound managed to show also the asymptotics for the fourth moment, which is of similar shape as in the case of the moments of theta. We have Q times log Q to power 4. And here, Heath-Brown showed this for in the case when Q doesn't have too many divisors, for instance, for prime Q and other Qs that don't have too many divisors, and sound extending it to all Q. And again, let's do the sketch for the upper bound. Morally, we can use the approximate functional equation to approximate L half chi by a Dirichlet series or character sum of length Q to half. And then by the large sieve, we get an upper bound for the moment with the L function replaced by this character sum. And now the large sieve gives an upper bound, which is the number of harmonics, which is Q, plus the length of the Dirichlet series whose square we are looking at. And that's the Q to K over 2, or length of the character sum. So that's Q to K over 2. And again, we get the mean square of the coefficients. And again, the mean square is of size log Q to K squared. So this gives us an upper bound of correct order of magnitude in cases the K is 1 or 2, which means the second and fourth moment in particular. This argument can be made rigorous to get an upper bound for the fourth moment of L half chi, and it's Q2 or Q fourth as it should. And actually this is almost easier than the case of the zeta function, because now we don't have the dependency on T on the approximate functional equation. But again, getting asymptotics is more difficult, and Sound and Heath-Brown and others have had to do some serious work to get them. But in any case, again, it's not surprising that asymptotics are only known for second and fourth moments. And I could also mention that now there's this sort of thing is known for instance for prime Q4 with an polynomial saving in the error term by work of Matt Young. Okay, so but in case of characters, we can add an additional averaging. It seems difficult to go beyond fourth moment in case if we average over chi. But now, if there's something that we can't do, we don't know how to handle in analytic number theory, usually we average and see what we can say on average. So here we can add an additional average over Q. We can look different moduluses as well as different characters. And in this case, we have an upper bound by Yard-Sieve, which is the number of harmonics Q squared plus then the length of the character sum again, which is again Q to K over 2, and then the sum mean square of the coefficients, which is log Q to K squared. And now if we look at the 2kth moment of L half chi, if we average over both the character and the modulus, we expect the asymptotic is about Q squared times log Q squared. So it seems plausible that we can get results up to K equal to 4. That is the 8th moment, because the upper bound is correct up to the 8th moment. And indeed, this way, we can get the upper bound for the 8th moment. We get the correct order of magnitude Q squared times log Q to 16. But getting asymptotics is again quite a bit more difficult. And this is what's the sort of the topic of my talk today. I will talk about asymptotics for the 8th moment of Dirichlet L functions when you average over both Q Q and chi. Okay, but before going into our results, I need to introduce some more notation. So first, we will concentrate on even primitive Dirichlet characters. This is still missing the word primitive, but it should be primitive. And I'm concentrating on even characters just for simplicity. I could just as well use odd characters, but it would change the completed L function and functionality equation a bit. So it's simpler to concentrate on one of the cases. So I will concentrate on even characters. And I write capital lambda for the completed L function. There I multiply the L function in particular by the gamma factor, which is the important part of the conclusion. And the completed L function, as usual, is defined in such a way that the functional equation for the L function takes very convenient form. So lambda at half plus s equals half lambda at half minus s apart from a root number which has absolute value 1. Okay, and still a bit more notation. I will use flat for sums that go over primitive and even Dirichlet characters. So I write sum of chi mod q flat for the sum where I only take primitive and even characters. And also I write phi flat for the number of even primitive Dirichlet characters. Okay, so before going to the 8th moment, let me say a few words about the general case and the 6th moment. So first, recall that we conjecture that if we look at average over characters and look at L half chi 2-gate moment, we expect that it's about the number of characters times log q k squared times a constant depending on q. And now recall the completed L function, which was L function multiplied by some stuff. And then Conry, Ivanets, and Sound have shown an asymptotic formula for the 6th moment of the completed L function when you average over the characters. Okay, there shouldn't be a flat here for the Q sum, but in any case, you take an average over Q and average over chi. And in addition, you just don't look at the L half chi, but instead you look at the completed L function and take an additional average over the y as well. In the t aspect, there is also an average. And for this, they have managed to show an asymptotic formula which corresponds to this conjecture in the case of k equal to 3. And there is another integral over the gamma factor because they are looking at the completed L function. But note that having this completed L function instead of the L half chi is not such a big difference as it might first look, because the gamma factor here decays exponentially in y. So the y average here, it has essentially a small support. When y gets large, this gamma factor starts decaying exponentially, and so the large y don't really contribute. This is much about L half chi, but we have to take a small average over the critical line as well in order to get this asymptotic formula. Well, Conry, Ivanets, and Sound had to do it. And for the 8th moment, as I said, by the heuristics, one does get the correct order of magnitude upper bound for the 8th moment. But what about asymptotics? There is a previous result by Chande and Lee, my co-authors, who showed a similar result for the 8th moment under GI8. They had to assume the general Riemann hypothesis to show a similar result for 8th moment as Conry, Ivanets, and Sound had for the 6th moment. But now we can get it unconditionally. So what we show is that if we average over characters chi and over the modulus q and look at the integral of the completed L function on the critical line, the 8th moment, then we do get the asymptotic formula that is expected. And if you really wanted to know, I can write the constant out here. It's this constant here. It's not very illuminating, but it comes from certain order product, essentially. Okay, so that's our theorem about the 8th moment. We still have to have this short t average here, but as I said, thanks to the decay of the gamma function, it's not too much. Okay. So let me explain why do we need the y average. Why can't we look at the eighth moment of the L half chi? Why do we have to take the completed L function and integral over y? So for this, I need some notation. I take GST to be the gamma product of gamma factors that appears in the eighth moment when we look at the completed L function. And then I need two sort of smooth weights. Don't care too much about what they exactly look at. I won't need them after this slide, but I just wanted to write them down anyway, so that if you want to see what they are, then you see. But I have this weight W, which decays exponentially in x to 1/4. And I have this weight V, which also decays exponentially when chi or eta is larger than mu squared. And then one can show approximate functional equations. First, for the L half chi to the power 8, we can have by an argument like an approximate functional equation argument. We can get that it corresponds to the Dirichlet series that defines it. When we look at eighth moment, we have tau for m and tau for n and chi n bar over square root of mn. And then for the approximate functional equation, we get the truncation with this smooth weight w, mn pi squared over q4. And we get the corresponding approximate functional equation for the integral, for the integral of the completed L function. And in this case, we have weight v here. And now if we look at the essential supports of these weights, we record these decay bounds for the W and V. So we notice that here we had exponential decay when x is getting large. So when mn is larger than q to 4, then in that case, this is getting very small. So essentially the support of m and n is up to q to 4. And in the second case, when we had the weight v here, if we look at the upper bound we had for v, we so notice that it is the essential support of the second expression is when m and n are at most q to 2, so the q squared. And this is the important difference between the case where we don't have a y-average and where we have the y-average. I will explain a bit more, but just forget about those annoying weights. Sort of morally, we obtained that L half chi to power 8 was the corresponding character sum truncated at m times n up to q to 4. And on the other hand, in the case where we had the completed L function and integrated over the critical line, we got that it's about the similar sum, but with m and n up to q squared. And now what is the difference here is that in case we have the y-average, we can restrict our variables m and n both to be up to q squared. And in the case when we don't have the y-average, we only know that the product is at most q to 4, which means that if we look at this thing here, we have to deal with some unbalanced cases such that m is about q to 3 and n is about q, whereas here we don't have to deal with such unbalanced cases. And this is the difference between the two cases. And when I talked about this in another question, I was asked about why can't we just apply the approximate functional equation, and why would we get such a strange restriction? Why don't we get also this sort of restriction in the case of just L half chi? But the issue is really the root number. When we take the when we want to use the orthogonal characters, for instance, we would have the tau chi's, the root numbers appearing there, and we can't handle them. So that's sort of the problem why we do get these different things in different cases. We are in trouble with the root numbers in this first case, which are complex. So here we are helped by the y-average because now we don't have to deal with these unbalanced cases. And there was the same story in case of the sixth moment, except that there the requirements are mn up to q cubed and m and n up to q over 3 over 2 respectively. But in any case, it was the reason why Conry-Sound and Ivanets wanted to have this short y-average was that they managed to avoid some unbalanced cases of the variables. They only had to deal with this case rather than this. But let me get back to the sixth moment for a second. So for that, actually also the unbalanced cases where just mn is up to q cubed seems to be doable. So we are working on this with Xian and Maxim, and this is more ongoing than the 8th moment. We are still working on the details, but we have the general plan and everything seems to work, but it's just very technical to get all of it through. But we think that we can remove the y-average in the case of the 6th moment and just look at the 6th moment of L half chi and then get the correct asymptotics. And this was previously known with the short y-average by the work of Conry, Ivanets, and Sound. I forgot to correct the typo here. So this should be Conry, Ivanets, and Sound. And in this talk, I will talk about the 8th moment. I don't go into any of the details of the 6th moment. This unbalanced case of the 6th moment is quite involved and quite technical, and it requires more tools. For instance, we have to use spectral theory to deal with some resulting Klustermann sums. We can't just use some results as black boxes. Morally, we know that things work thanks to these existing results, but we have to also due to some technical problems, we have to go into the details of these things. So it's quite technical, and I'm not talking about it today, but I will go back to the 8th moment and talk about this case of the 8th moment where we do have this additional t-average on the critical line. So this was our theorem for the completed L function. We have the asymptotic formula for the 8th moment. And what I will do is I will sketch the proof. I will forget about many technicalities. I will try to make things as simple as possible with still keeping the main ideas visible. So by what I said before, by the approximate functional equations, we need to study something like the corresponding Q average and chi average, and then sum the truncation of the character sum with m and n going up to q squared. So that's what the approximate functional equation gave us. In practice or in reality, we have this weight v here, which makes things a bit more sort of technically annoying, but I won't care about that in the talk. I will just think that we can truncate at m and n going up to q squared. Okay, so that's the sum we want to study. And this looks like sort of things that we do in analytic number theory with large sieve and stuff. And if we just wanted to get an upper bound, we would be actually finished with using the large sieve. But of course, we wanted an asymptotic, so it's not enough to use the large sieve. But the large sieve is still helpful. At this point, we can use it to truncate our sums a bit. So we first notice that if we restrict the m sum here, say to be from q to 2 minus epsilon to q squared, then we can use the large sieve to get an upper bound for this. And by the large sieve, it's the number of harmonics q squared plus the length of the sum q squared times the mean square of the coefficients. Okay, I'm missing the square here apparently. This should be tau for m squared. And then calculating the mean square here, we get that this is epsilon times q squared times log q to 16. So the mean square of the coefficients is log q to 16 times epsilon, thanks to this restriction that m is between q to 2 minus epsilon and q squared. And we are having this 1 over m here that saves us a factor of epsilon, which means that we can truncate to m and n up to q to 2 minus epsilon. The values larger than 2 to q to 2 minus epsilon give a small order of contribution. This is actually the point where our error term comes from, why we can't save very much in our error term. In practice, we will actually, in our paper, we are choosing the lower bound of the truncation to be q squared over x log q to epsilon. And in that case, we get an error here, which is log q to 15 plus epsilon, or something like that. So this is the actual error term in our theorem is here we get the main term is of order q squared log q to 16, and the error term is q squared log q to 15 plus epsilon. And that worst error term comes from the truncation. But for the purposes of this talk, I'm just trying to get an error term of E2 of 1, so that's why it suffices to have the truncation at q squared divided by q to epsilon. So this is the sum we have to now consider. We have truncated up to q to 2 minus epsilon, which will be very important later. And the first step here is then to use the orthogonality of characters. So now there's a bit of technical complication because I'm only summing over even primitive characters, but by using Möbius inversion, one can get an orthogonality relation also in that case. And the orthogonality relation looks like this. It becomes the sum of divisors of Q, and then M and N are either congruent mod R, the divisor R, or M is congruent to minus N modulo that divisor R. And here we have mu D pi R from the Möbius inversion. But for simplicity, I will concentrate on the case that R equals to Q, and this plus minus sign is minus. So note that here we have mu of D, which has absolute value at most 1, and phi of R, which has absolute value about R. So the case where R is large is the most significant one. So I will concentrate on the case there R is actually Q, and in the case there M and N are congruent mod Q. So this leads us to the sum where I sum over Q, and I have the phi Q from here, and I sum over M and N that are congruent mod Q, and then I have the four divisor functions as before. So this comes from here if you just pretend that I'm summing over all characters and forget about even and primitive ones. Okay, and now here the diagonal contribution, the M equals N. It leads to a part of a main term. It's a bit more complicated because we have the weight really here, but in any case, I will concentrate on the case there, on the non-diagonal case there, M and N are different from each other. Okay, so this is the sum where we got by now. We have the sum over Q's, the modulus, and we have the sum over M's and N's that are congruent mod Q that are not equal to each other. And the next trick we want to use here is the complementary divisor trick. And this was also used by Conry, Ivanets, and Sound on their work on the 6th moment. And here, okay, I should say that actually most of the things that I'm doing was also used already in the work of Chande and Guy on the 8th moment. And also on the other hand, their work is going back to the 6th moment. So we just have to make the conditional steps unconditional in their proof. That's the difference between my work with that of Phi and Xianon. Okay, so the next step is the complementary divisor trick. So we write this M equal congruent to N mod Q here as M minus N absolute value being H times Q. And then we replace the condition mod Q by a condition mod H. And this gives us to sum like this. So instead of summing over Q, we now sum over H, which is M minus N over H. And note that because M and N have size at most Q to 2 minus epsilon, and Q has size about Q, we know that this H must be at most of size Q to 1 minus epsilon. And then we are still summing over M's and N's up to Q to 2 minus epsilon. And we change the congruence condition M equal to N, congruent to N mod Q as a M congruent to H, M congruent to N mod H. And we get an additional condition from here because we had the condition that Q is of size Q from Q to 2Q. That means that M minus N is between H times capital Q to 2H times capital Q. So that's an additional condition we are getting from the complementary divisor trick. And then we have this same sum as before. And just expanding back to characters. So we had a character sum, and then we went to a congruence condition. Now we made the complementary divisor trick, and now we want to go back to character sum. So we expand the condition m equal to n mod h as a character sum mod h, and then we have the same thing, except that now we have this characters chi m chi bar n here. And what's the point? Why did we want to go back and forth? The point is that we have managed to make the modulus smaller. So the q was of size q, but now we have the modulus of the characters is of size at most q to 1 minus epsilon. So we have a factor of q to epsilon in the size of the conductor, and that's a crucial point. And for this, we needed the truncation with the large sieve at the first place, because beforehand, we wouldn't have had, if we had the condition that m and n go up to q squared, then this would help us at all, because h could still be of size q. So we would haven't got anywhere, but now we have managed to drop the conductor a bit, and that will be crucial for our work. Okay, so this is where we got by now. We had this sum over h's and the sum over characters mod h and sum over m's and n's with m minus n restricted to this interval. And again, we just get some main contribution. The principal character chi naught gives us a main contribution, but let's not care about that. Let's concentrate on the more difficult case of the error terms, which are the non-principal characters. And now notice that we had this condition that m minus n is between hq and 2hq. And this means that we are looking essentially sort of a problem on almost all short intervals. We are looking at the sum of m's and n's that go up to q to 2 minus epsilon, but we have a restriction on the difference of m and n. The difference of m and n is from hq to 2hq, and in particular, if h is pretty small, like if h is 1, then this restricts the difference of m and n to be from q to 2q, which is quite a bit smaller than the size of m and n. So this is sort of a problem for things in almost all short intervals. M and n are going quite widely from 1 to 2 q to 2 minus epsilon, but we restrict that they have to be close to each other. And this can be morally written in another form as we have this same things in the beginning, but instead of having these conditions m and n going up to q to 2 minus epsilon, we are looking at each interval from x to x plus 2hq, say, and then we are taking a square of things in that interval. This gives us m and n in the close to each other, and then we are integrating over our x's. This is not quite the same, but we can say we have the smooth weights here, and we can use Mellin transform to get into the same conclusion as by doing this thing that morally makes sense. If you square this out, you get terms like this and some other terms, but this can be made rigorously, this thing. And just moving some factors to make this normalization making sense, we can write this in a form like this. So we have come to a problem in almost all short intervals. So this is what we need to study. We have a sum over h's, the modulus, the sum of the characters, and then we have an integral over x's, and then we have an almost all short interval question about tau for m. And this is actually quite familiar from studying arithmetic functions in almost all short intervals. Say, if one studies primes in almost all short intervals, then one gets an expression like this. And if one studies primes simultaneously in almost all short intervals and in arithmetic progressions, then it's exactly like this, that one obtains just instead of tau for m, one has the indicator function of the primes. So this is quite familiar. And in that case, there's a standard way to attack things. The standard way is to use first Perron's formula here to translate this as an integral, as a contour integral, and then use a Parseval type of argument, or just square out and integrate, which reduces the thing like this to a mean square of a Dirichlet polynomial, of a corresponding Dirichlet polynomial. So by using what one does, by doing what one does for primes in almost all short intervals or so on, one can reduce this into the mean square of a corresponding Dirichlet polynomial. And here the important parameters are the modulus, which is h, and then the length of the integration of the t aspect is the sort of the size of the x's, which is q to 2 minus epsilon, divided by the length of the interval, which is hq. So it's the t is q to 1 minus epsilon over h. And what one needs is to show that this mean square here is smaller than q to 2 minus epsilon times log q to 16. And there was some hand waving in the steps here, but what one actually can do is, as I already briefly mentioned, is to, here we had the smooth weight, one can use the Mellin transform of that smooth weight to get directly here. There are some step in between, but it doesn't go through the really almost all short interval thing like this, but you can just work to get into the same conclusion that this is what is needed. Again, there are some weights, but don't care about them. No. Here. So this is what our game reduces to. We need to have this mean square of the corresponding Dirichlet polynomial, and we are summing over the modulus and the characters. And perhaps I should point out that this is not so much different from what we started with, and we could actually replace this by L half plus IT chi to the power 2 instead of introducing the fourfold divisor function, and we would have about the same thing as what we started with. We would have an 8 moment average over t and h and so on. So this is very similar to what we started with, but we have managed to reduce the conductor here, and we only need an upper bound now. We have already taken out the main terms, so we don't have to care about them anymore. So that's the gain we have made. And here the t is of size q to 1 minus epsilon over h. And now one can apply the hybrid large sieve to this expression on the left-hand side. And this gives us the bound, which is the number of harmonics, which is now h squared times t, plus the length of the summation here, which is q to 2 minus epsilon, times the mean square of the coefficients, which is log q to 16 here. And recalling that t equals to q to 1 minus epsilon over h, and that h is at most q to 1 minus epsilon, one gets an upper bound of size q to 2 minus epsilon times log q to 16. And thus this, of course, barely fails. We wanted little of this, and we got bigger of this. So we are very close to what we wanted, but we didn't gain anything compared to the sort of the trivial bound that we had in the beginning. And now this is very familiar from my previous work with Maxime on multiplicative functions in almost all short intervals. There we didn't consider the h aspect or q aspect, but we had a similar situation where we had the mean square of a Dirichlet polynomial, and we wanted to win a little bit over the trivial bound. And the mean value theorem gave us a trivial bound, which just was sort of what we needed, and we managed to make a strategy that works in such cases. And this was our initial idea, and it does work. One can sort of here restrict to numbers that have a typical prime factorization, that have prime factors in convenient intervals, and then one can use these size factors of different sizes in order to get the final result that we want. But actually this is not needed. We later realized that this question is easier now that we have tau 4 here instead of some general f. And what we can do, we can use the approximate functional equation to approximate this L, this sum here, which is a partial sum of L s chi 4 by a same sort of Dirichlet polynomial, but with length which is the square root of the conductor of this L function. And the square root of the conductor of this L function is h times t squared, which is q to 2 minus 2 epsilon. So now we had a sum of size q to 2 minus epsilon, but thanks to the functional equation, we can truncate to a sum of length q to 2 minus 2 epsilon. And that makes a big difference, because now in the hybrid Gaussian, the second term here will be q to 2 minus 2 epsilon. And actually the first term is also at most q to 2 minus 2 epsilon, which means that at the end we get q to 2 minus 2 epsilon. So it is little of q to 2 minus 1 epsilon, or q to 16. So now the hybrid Gaussian turns out to be sufficient alone without having to repeat any of my work with Maxime for multiplicative functions in almost all short intervals. So this is the step where we avoided needing the CIH, was really the reduction to this mean square. So in the previous works, people haven't worked so carefully with the Mellin transforms. The functions are a bit complicated, so it's a bit difficult to see what's really going on. And they have ended up with double integrals. And in that case, the bound coming from the hybrid Gaussian is not sufficient, but instead they had to use generalized Riemann hypothesis to get an more or less optimal bound for this. Okay. So that's the way we get the result for the 8th moment. So we do get the asymptotic formula once we average over Q chi and a short average on the critical line. As I said a couple of times before, this average is short because there is the fast decay of the gamma factor, which makes this integral to be concentrating around t equal to 0. But we get the asymptotic formula for this 8th moment. And this is ongoing work with Faixian and Maxime. And we have a more ongoing work where we work with the 6th moment and where we managed to avoid the additional t average by working out the unbalanced cases, which is very technical. So this is what we have got so far. And one can ask what else? Are there other things we can do? And yes, there are some other things. First, pretty easy thing is that we can also work instead of Dirichlet L functions. We can look at the L functions corresponding to a holomorphic modular form twisted by Dirichlet character chi and look at the completed L function. And in the same paper where the Fai and Xanan studied the 8th moment of Dirichlet L functions, they studied the 4th moment of the completed L functions corresponding to these objects. And they had the result on the CIH, which gave the asymptotic formula for the 4th moment. And the method is essentially the same. They are repeating the same arguments. So this should also be unconditional now. There seems to be no obstacle in making also this result unconditional. And another thing that we are currently investigating or starting to investigate is the modified moments of Dirichlet L functions. So we want to find out if we can make the modifiers of Conrivanets and sound longer in case of by using perhaps some of the ideas from the work we are doing on the 6th moment on the unbalanced cases, but that's just something we are beginning. And also we would like to remove the t average from the 8th moment, but not sure. It seems difficult to do that. Okay, but that's all I wanted to say. Thank you and happy birthday.
Okay, thank you very much. Thank you very much for a very nice talk, very nice results. Kiitoksia paljon. I have a question. Maybe I start with this question. I am sure. It's the following, that you have a main term. Let us say it is a constant times a lot of things. Possibly there is some expansion of this term as a polynomial in 1/log q or something like that. Have you some idea, some project on that side?
Yeah, I think so. But with our method, we can't get into the lower powers because we have to do this truncation step, which loses us so much that after that we can't hope to get a term of the sake of q to 15 because there we lose something.
Can you, however,
but
sorry, please,
but I think in the case of the fourth moment, for instance, the Young has an asymptotic formula with the power saving. So in that case, there is a correct expansion.
Can you say, however, some power of a log in the arrow term? The little o of 1, is it a little o of 1 over log q to some power, even a small one over square root of log q or something like that?
So it's log q to minus 1 plus epsilon.
Yeah, okay.
That's what we get. Yeah.
That's what I understood. Okay, thank you very much. Are there other comments, questions?
Can I ask a question?
Yeah, sure.
Yes. Sorry. So yeah, it's very nice that you work this out for eighth moment, which I think is a pretty high moment. So I mean, it seems like this new method again meets like more or less the limit of this moment. So I wonder if, okay, so if that is really the case, then which part of the argument starts to fail for when you want to work with higher moments? Is it the truncation for the sum over m and n, or this truncation with the for the sum over modulus, which actually is like the limit of this method that you cannot go for higher moments?
Well, it's really the fact that from the sort of approximate functional equation, you get a too long polynomial here. Like the heuristics I showed at the beginning, we don't get even upper bounds for the higher moments. So if we had, say, the 10th moment, then we would have q to 5 over 2 here instead of q squared, which would mean that here we have q to 5 over 2, but we would still need a bound like q squared here. So that's the problem.
I see. I see. So it's pretty much like the best possible moment that we can work on with this type of average moments.
Yeah. So it's the same issue with the zeta function. For the zeta, we can do only the fourth moment because then we get into trouble because we don't even get an upper bound.
Yeah, I see. Thank you very much. That's very interesting.
Yeah, no problem.
Okay, thank you. Are there any other? We have some time. Are there other questions, comments?
May I ask a question?
Yeah, sure, Igor.
Hi guys, it's Igor. I have a small technical question. When you do this truncation and you apply the large sieve, you apply it to polynomials with coefficients of very different sizes. Is it not better to slice it first into dyadic intervals and then apply the large sieve?
Well, actually, we do slice it to short intervals and then apply large sieve. I was just not giving all the details.
Oh, okay. Yeah. Okay. Thank you.
Thanks. Some other question? Well, if not, thanks again, Kaisa. And okay, organizer now have the hand.
Thank you, Professor Dejue, and thank you, Professor Matomaki. Now the next two chairs will be chaired by Professor Rudnick. I hope he is here. Not yet, but we still have 10 minutes. So we resume in 10 minutes. Chantal, if you want to check the screen, if your slides, we can do that.
I can do that now, absolutely. Yeah, it's better to do it
yeah, I can.
Sooner than later, in case it doesn't work.
It works.
Yeah, thank you. So we start at, well, 8 for me, but in 10 minutes. Is it correct?
9 minutes, yes.
9 minutes, yeah, exactly, yeah. in those area, yeah.
I shouldn't
So
We're saying, hello. That's a very official background. It's like you're part of the Olympic Committee or something like that.
yeah, that's right. I can change it if you want.
That's okay. That's okay. But it looks very
Is
official.
that
Like you're
background what you have?
about to do a press conference or something, you know?
Okay, I'll change it. I'll make something.
It looks very official.
How's this?
Yeah, that's less official, I would say.
Okay. That's my house. I'll keep my house.
How are you? What time is it for you? Oh, it's about the same time as Europe, huh? Yeah, so.
It's almost 2. So we are 1 hour back of Central Europe. Back of it. Yeah, how are things in Montreal?
Yeah. You know, this is of course, we have a big lockdown, but now it's getting better. Vaccination is very slow, but my mom is getting vaccinated next week. So after next week, I'm going to be
Okay. Of course, you are not.
65 and more, but I don't know how much time it's going to take them to finish that, you know?
Yeah, my brother lives in Nova Scotia, in Halifax, and he's a physician, he's a doctor, and he's not yet been vaccinated.
Oh my God, that's terrible.
Yeah, very slow.
It was in the first category. People who work in the health system were in the first category, with people in old age home were the first, and yeah.
Right, no, but he's a psychiatrist, so they figure that it's less urgent.
Okay.
But it is taking a long time.
Yeah, for example, dentists or optician, you know, they're all on your teeth, on your eyes, and they're not vaccinated yet. That's very weird.
Yeah, that is weird.
Yeah.
Yeah, because they're actually in great danger. All right. So you just have to be careful.
Yeah. So like I can see my mother because she's alone, so she's allowed to have one person. But like this weekend we're going to the country, but I don't think I want her to come because she's getting her vaccine. So even if she gets a little cold, it will delay the vaccine. So now we feel that we have to be very careful.
Yes. And then she has to wait until she gets the second dose, another couple of weeks after the second dose until it's reasonably safe.
Vaccine, you know, that they're giving now, they say it's more efficient if you give the second dose actually after 3 months.
Really?
I don't remember what the name, but this is what the study show. So that's
okay.
good.
Now here they gave everyone the vaccine, the second dose after 3 weeks.
Yeah. Well, it's not all of them, but you know, for some of them they did studies saying, okay, when, because they're kind of not really sure about that, you know, and it seems to indicate that it's more efficient after a couple of months.
Okay. For us, everyone has gotten, most people have gotten the second doses a while ago, but they spaced them 3 weeks apart. But maybe it's a different kind.
Well, don't complain. I'm still waiting for my first dose. My mom is still waiting for her first dose.
Yeah, that is depressing.
Don't complain.
No, but you know, the funny thing is my mom was vaccinated like 3 months ago. But she's a transplant patient. She had a heart transplant 25 years ago, but she's still on immunosuppressant drugs. And they ran a serological test for antibodies a couple of weeks ago, and they said they didn't find any. So they suspect that the vaccine didn't work.
Oh, because of the condition. Yeah. Okay. Yeah.
Yeah, which is bad news. It means she has to stay very careful until it's reasonably safe to go out.
Yeah, I agree. Yeah, it's also. Is it me? Sorry.
I hope not.
My daughter, who didn't text me like for weeks now.
Okay.
Now it's like that.
No, you know, the funny thing is that
this past few months, I've been attending about 7 seminars per week.
Yeah, it's too
Really
much.
saturated now.
Yeah, completely saturated. Yeah, I think, when was that, yesterday? Some student canceled, so for the first time in weeks, I didn't have any Zoom meeting. You know, this is like, oh my God, a day without Zoom meeting is now a
Yeah, it's
rare.
not, you feel you haven't earned your keep.
Yeah, I
It
feel
is
like,
fine.
you know, I'm kind of working more because there's no excuse not to meet your student because you're away or this or that. So you always have to.
Exactly. And you have meetings at, it's 10 p.m. and things like this.
Mm.
It is in some sense more efficient because you don't waste time, but you are more available. And there's
Yeah.
a downside to that.
Is it a good thing?
Not clear, not clear. Not clear.
Definitely more available, unfortunately.
Yeah, that's true. It's true. So who was Guloglu? I've never met him.
Oh, he was a student of Luo. I met him
Okay.
because he was a postdoc for 1 year in Kingston. And
Okay.
that's someone who did a talk in Kingston, well, 2 years ago, not a long time ago. Yeah, and we started working on that. And actually, we were supposed to do that work in Turkey because he got a grant that I would go there for a month. So,
Okay.
so when we
We'll have to wait.
But I think there's 3 years for that. So.
Right. I think a year from now it'll be okay, but not before.
That's okay. Yeah. You know, I think we're gonna take it step by step. Just, you know, vaccine, normal life. Listen here, restaurants are not open yet, so we're really a long way from the.
This week is the first time I've been to a restaurant in a while because things have opened up here. So, but only recently. It'll take a while.
Yeah. I feel like I became less social, more lazy, you know, more stay at home.
Exactly, because you just get used to staying at home, having Zoom meetings and Zoom conferences. And
I think maybe I'm gonna feel, oh, let's meet on Zoom. I don't have to go out.
That's right.
Hello, everyone. The next two talks will be chaired by Professor Jim Rudnick. So over to you, Professor Rudnick.
All right. Welcome back, everyone. I think we still have, according to my clock, 1 more minute. So I'll let people settle down, get their chairs. I see several names that I know. And our speaker right now is Chantal David from Montreal, which is an insanely cold place. And she will tell us about one-level density for cubic L functions. Go ahead, Chantal.
Thank you very much. Thanks, Zed. And I'd like to thank the organizer and, of course, happy birthday, Balu. That's actually my second Balu Fest. The first one was, and a lot of people here were there, 5 years ago in Chennai, which was very nice to be there. It's nice that we have an occasion to meet on Zoom, but I guess I'm going to wish in 5 years in Chennai, not on Zoom, for the next one. So the work I'm going to talk is joint work with Ahmed Guluglu. So one-level density for cubic Dirichlet L function. So the one-level density is done for a family of L function, and this talk is going to be Dirichlet L function. Well, cubic L function, but I'll give example with quadratic L function. The one-level density measure the densities of the zeros on the critical line, s equal 1/2 plus it, the low-lying zero around s equal 1/2. So following the word of Montgomery and then Kaczmarek, we believe that statistics on the zeros of L function would match the statistics on the eigenvalue of random matrices in certain symmetry groups determined by the family of L function. So unitary, symplectic, or orthogonal. So the one-level density being one of those statistics, this is what it's believed to match the statistics of eigenvalue of random matrices. So to state that more precisely, let me define things properly. So W and phi will be even Schwartz function. F is a family of L function attached to Dirichlet character ordered by the conductor. I'll denote by C chi of the character. And we consider the count of characters or family in the L function and the smooth count. So that's going to be the summation over the character in your family of W of the norm of the conductor divided by X, which is the smooth count of the number of L function of character with conductor up to X. So I wrote the norm because I'm going to work over Q adjoint the third root of unity. So it's going to be the norm. So if you fix an L function, for the one level density, I need the sum over the low-lying zero, which phi is a Schwartz function. It decays very fast. And you normalize them properly. So if the conductor is about X, you normalize the imaginary part of the zero by multiplying by log X. So the count over the low-lying zero would be the count over the 0, 1/2 plus I gamma, such that L rho chi is 0, phi of gamma log X divided by 2 pi. Okay, so moving on to define the one level density. I'm very slow, maybe because in Montreal it's very early, so let's define everything slowly and properly. So the one level density, first of all, let's sum all the character of the family with conductor up to X, and let's average over that this count of the low-lying zero, which is the first line I wrote. So dx phi f will be 1 over the smooth count over the family, and now you're averaging this count of the low-lying zero. So taking the limit as X goes to infinity, you get the one level density. So again, that's a statistic would give a density for the low-lying zero. Everything is normalized so that it actually gives a number. So the conjecture of Katz-Sarnag is that this low level, the one level density, this limit, is going to be the integral of the test function versus some kernel, which measure the one level density on a group of random matrices, which depend only on the symmetry type of the family. So the statistics on the zeros of the L function will match the statistics on this group of random matrices. So I just repeat the conjecture on that slide. So the conjecture is still open. What I'm going to discuss in that talk is partial results or evidence for this conjecture can be obtained by showing that the conjecture is true for certain test function and test function phi where the Fourier transform would have limited support. So this is the type of result I will describe in this talk. And I want to talk about cubic character, but let me first state the result for quadratic character and compare them. So the result for quadratic character is due to Oslo and Schneider. So F2 will be the family of Dirichlet L function attached to primitive quadratic character. So those would be the Kronecker symbol AN. I'm going to take N odd and square free. So in that case, they got the conjecture is true for phi such that phi at is supported in -2, 2. And this is the result of the GRH. So assume GRH for all the L function in the family, then the one level density, this limit, is indeed given as the conjecture of Katz and Sarnag by the integral of the test function versus this kernel, which measure the one level density for symplectic matrices. Because the family of quadratic character you can see as symplectic symmetry. And of course, the right-hand side can now be computed explicitly because we know what is the kernel of the one level density for symplectic matrices. And you can compute that and it's going to get phi at 0 minus 1/2 of this integral. So it would be, this, of course, this integral would be different if you change the kernel. For unitary matrices, for symplectic matrices, it would be different. Okay, so this is the result for the test function supported in -2, 2. So one application of that is that if we know the one level density and the support of the Fourier transform is large enough, we can show that there's a positive proportion of L function in the family which do not vanish at the central critical point. Okay, you're looking at the low-lying zero, so it makes sense that using those results, you can say the result for the vanishing at the point 0. And in the case of it's conjecture by Chawla that L1 half chi should be non-zero for all L function attached to Dirichlet character. So he originally conjectured that for quadratic character, but then it was extended for all L function of all Dirichlet character. if you use the conjecture of Katz-Sarnak, I wrote the full conjecture, I mean, without any limit on the support of the Fourier transform, this will imply that L1 half chi is not zero for all L function in a family except a set of density 0. And in fact, the conjecture of Katz-Sarnak would make sense over number field and function field, and over function field actually. Sherlock conjecture is not true. So the except a set of density 0 is a good news from that point of view. So over function field, recent work of Lee would show that there are infinitely many quadratic characters such that L1 half chi is equal to 0. But of course, that's a set of density 0. And this was extended to characters of order L prime by Deneuve and Lee. So what's the corollary of the theorem of Oslo-Schneider? So there's a support of -2,2. So what's happened is there's a formula from the one level density, an easy computation you can make. So given a support in -VV, there's a little formula which gives you the proportion of non-vanishing. So for the family of quadratic character, and again, this is a result on the GRH, the fact that you have support in -2,2 gives you non-vanishing in 15. So for a proportion of 15/16 of the L function in the family. And I wrote the little formula that 1 minus 1/2 1/2V squared. If you put V equal 2 in that, you'll get 15/16. So I wrote that formula because for cubic, which is a unitary family, you'll get a different formula, which makes that it's easier to get a positive proportion for the same. It's more difficult to get a positive proportion for the same support of the Fourier transform because the formula is different. So I'm not going to talk more about that, but I should mention the result, that the result of Oslo and Schneider is unconditional. It's conditional on the GRH, I'm sorry. Unconditionally, Sandar-Arajan proved that L1 half chi is not 0 for 7/8 of the quadratic L function by a different technique, by computing the first two modified moment over the family, which is, related to what Kaisa was explaining in her talk. So if you can compute the first two moments and you need the modified moment, you'll get result on the one level density. I don't know why this thing. I'm sorry, I'm afraid I have a shift in my slide, but I'm afraid of pressing a button. I'm sorry about that. Okay, so the result I want to present in that talk, the work that I did recently with Ahmed, is improving the support of the Fourier transform for the one level density for a family of cubic character. I would explain in the next slide that -1,1 is kind of the GRH trivial range. So the game here is to beat -1,1. For quadratic character, it was beaten to -2,2. Here we can get -13/11, 13/11. So that's the result. If you take a test function such that the Fourier transform is supported in -13/11, 13/11. And now we take a cubic family. So when you take a cubic family, well, you have to say which family we mean. And the family I call F3 prime, you're going to see later why I call it like that, is the family of cubic residue symbol chi n of A, which is the cubic residue A over n, where I take n and z omega square free and co-prime to free. So it looks very much like the family of quadratic character, which were the Kronecker symbol A over n, where n was square free. Now you're over the Eisenstein integer. So assume the GRH for the L function in the family, then the one level density, according to the conjecture of Katz-Sarnak, for those special test function is indeed given by the integral of your test function versus some kernel. And then the kernel is the kernel for the one level density of unitary matrices. So first of all, the one level density is different. If you remember that for symplectic matrices, which was quadratic character, it was not phi out of 0. There was another term. And also the formula which relates the support of the Fourier transform to the proportion of one vanishing is different. Here it's 1 minus 1 over V. So if V was equal to 1, you would get nothing. As if you try V equal to 1 in the case of quadratic, you would get something. So because we get a support of 13/11, you immediately get a proportion of non-vanishing of 2/13 by putting in that formula.
Chantal, may I ask a question?
Oh, I was to say, if there are any questions, please ask. I was
Yeah,
reading
this is the time we arrange it. So if I remember correctly, for the quadratic case, you can get half the range without the GRH.
Yeah, you can get a result without GRH, yes.
Right.
Yeah.
So if I remember, in the quadratic case, you get half the range, which gets you to -1, 1.
Yeah.
And in the quadratic case, that gives you, as you were saying, a positive proportion.
Exactly.
And here, what can you get without GRH?
I don't remember when we, I mean, I don't remember, but it's in our paper. We wrote it in our
Okay,
paper.
there is a range that you can get, but
Below -1, 1, you don't get any result. Yeah. Yeah. So GRH being Lindelof. So at some point, if we don't use Lindelof or we use, some kind of other bound, you're going to get, you're going to see, because I'm going to do part of the proof and you're going to see that, but without GRH, you don't get anything. Yeah. But you remember the formula for quadratic, you don't need a big V to get a positive proportion. The formula here is very different. Okay, so this extends the trivial range, -1, 1 for the one level density. And as I'm saying, and Zev was pointing out, it's necessary to beat -1, 1 to get a positive proportion because we have unitary symmetry. Okay, I said, okay, my cubic family is, cubic residue symbol A over n, where n is square free. Okay, what is the family of cubic character? And in fact, this is when you read a paper on that, first you need to find out, okay, what it is. For quadratic character, it's simple, but for cubic character, there's more case. First of all, the family is different in the Kummer case or the non-Kummer case. If the ground field contains the cube root of unity, which actually is a very natural case for cubic character, or not. So over Q, the ground field does not contain the cube root of unity, so that's the non-Kummer case. So it's different, and also the count is different. If you look at the cubic character over Q with conductors smaller than X and you count them, you're going to get a constant times X. And if you look at cubic character over Q omega, which contains the third root of unity, so such that the norm of the conductor is smaller than X, you would obtain X1. And that's easy to see why. Because over Q, there are going to be 2 cubic character of conductor P for each P congruent to 1 mod 3, because it's clearly a necessary condition. So if your prime is congruent to 1 mod 3, you can define the cubic residue symbol mod P exactly the same way as you would define the Legendre symbol. So AP3 will be you raise A to the power P minus 1 over 3. So 3 has to divide P minus 1, and you look at that mod P. So of course, that's going to give you a third root of unity in FP. So you have to associate it to a third root of unity in C, and this choice is completely non-canonical because the third root of unity are not in Q. So over Q, you cannot really say, okay, this one is the cubic residue symbol, and this one is its conjugate. You cannot distinguish them, but you do have 2 of them, which is what I wrote. So over Q omega, there are 2 characters in conductor pi for each prime. So the norm of every prime is congruent to 1 mod 3 there. So there's the cubic residue symbol, which there is canonical and it's conjugate. Okay, so, and now that explains those formula. Over Q, there are 2 characters per prime for half of the prime. It gives a constant times X. And over Q omega, there are 2 characters per prime, which gives X log X. The generating series will have a double. Okay, and what's the family F3 prime? So, because both of those family, over Q, it's kind of not natural. Over Q of omega, there's a lot of characters, so everything is a double sum, which is more difficult to deal. So it became customary to consider this family, which is a subfamily of density 0 over Q omega, which I call F3 prime in that talk, which is the set of cubic residue symbol AN, where n is in Z omega square free, and the norm is smaller than X. So first, the number of those cubic characters is a constant times X, so it's a thin family of the whole set of cubic character over Q omega. Okay, so what is the previous work on the 1 level density? So for cubic character over Q, it was done by Messner. And for the subfamily F3 prime, which is usually what is considered over Q omega, but show in part. And in both cases, the support of phi add is contained into -1, 1 under GRH. That's, just, writing the 1 level density, using the explicit formula, writing Perron, and doing things the way you think you would do, and using Lindelof. Okay, that naturally leads to -1, 1. And also, as Zev was mentioning, both paper and also in a paper of Guy and Zhao also have unconditional result. Okay, if you don't use Lindelof and you replace it by something else, you would get something which is smaller than -1,1. I didn't write, but you would get something smaller. Okay, on the related topic of moments, I just want to say, okay, which result I know for cubic. Again, for moments, the first case that was addressed was this tin family over Q omega. It's similar to quadratic, you know, it's not a double sum. So that was done by Luo and Friedberg, Oftun, Lehman. So the second case that was considered for moment of cubic character was cubic character over Q by Bayer and Young. And this is less natural because the cubic character really don't live over Q. You don't have a third root of unity. So you need to, when you consider this family of character, you kind of need to go over Q omega, and you have unbalanced sum. One of them is over Q, one of them is over Q omega. So it's less natural. So it's more difficult to obtain those results. So if you want to go to full family F3, I think it was only done over function field by me and the Floria and Lalun. So in both the Kummer case, which is the equivalent over Q omega, which actually was not done over number field, and the non-Kummer case, I'm sorry, which is the equivalent of the result of Bayer and Young. Okay. So it's customary to do this family F3 prime over Q omega, but you can also do the full family. Okay, as for the proportion of non-vanishing, this is not the result I want to talk today, but the reason I mention it is, so we obtain a result for a positive proportion of non-vanishing in the family F3 in the non-Kummer case over function field. So this is the equivalent of Q. And in that case, I don't know how to do the one level density. I don't know how to break -1,1, either over function field and number field, but you can do another technique, which is actually more involved, by computing the first modified moment and sharp upper bound for the second modified moment. So that would be how to get a positive proportion over Q, if you translate it over number field, which is not what I'm presenting today. And a feature of those results is that the proportion is incredibly tiny. Okay, that's the positive proportion that we get. 37 times e to the minus e to the 182%. Okay, as of course with the one level density, you get a proportion which is much more humane, so to say. Okay, are there any more questions? So after I did this review of the result that are obtained, I'm going to concentrate on explaining our result. And maybe the first thing I'm going to do is let's do this result, which we didn't find in the literature. Let's just take the full family and compute the one level density. Okay, the full family over Q omega is going to be this double sum, and we're not going to be able to pass -1,1. So, but let's explain how we do that, and then I will explain how do we improve if we consider the tin family F3 prime. So let's take the full family of cubic character over Q omega. I don't know why there's always a bracket, so it should be a parenthesis. It just annoys me to see that now. Assume the GRH for the L function in the family, then the one level density is given by the conjecture of Katz-Sarnak if the test function is supported in -1,1. So let me explain how to get that result again for the full family. That's why it's mine. I told our result was 13 over 11. So now this is the full family. There's no prime. That's why it's only -1,1. Okay, I'm repeating that at 10 times. You cannot get any positive proportion in the full family because the support needs to be larger than -1,1.
I'm sorry, Chantal. So I mean, since this is appearing a few times now, I would like to ask. So you mentioned about breaking this support being only in between -1,1. So does it mean that if this phi, the Fourier transform of phi is supported in a larger range, then you can actually get a better proportion?
No. It means if the support is in a better range, the error term is bigger than the main term somehow. So we don't get anything. I'm gonna explain it actually, because I'm gonna go through. There's gonna be a bit of analytic number theory 101. You know, for me it's very early in the morning. That's my excuse. So you're gonna see that.
Oh, sorry. Yeah, thank you.
Okay, so let's try to explain this theorem and then move on. How can we improve for our family? So okay, so I'm over Q omega, so I have to take a KL function. So let me take let's say you have a primitive Eke character of conductor C over Z omega, and this is the L function, you know, the sum over chi A over norm of A over the ideal, or it can be factored as a product over the prime ideal. And then for those functions, the completed L function, lambda of S chi, where you have, you know, the conductor to the power S over 2, you have the gamma factor in the L function, it satisfies a functional equation. And the functional equation, now I would say I have character which are not necessarily quadratic character, so it's not necessarily self-dual. It relates the L function at chi to the L function at chi bar, and it relates, of course, the value at S to the value at 1 minus S, and there's a sign of a functional equation. So for quadratic character, chi bar is chi, the sign of the functional equation is 1, but in general, it's not, and this is the case I'm studying. The sign of the functional equation is given by a Gauss sum. So it's the Gauss sum divided by the norm of the Gauss sum, so it's really something of modulus 1, and the Gauss sum is this mix of additive and multiplicative character. You go up for all the alpha mod C, you do chi of alpha times this, you know, exponential of the trace of alpha divided by C. Okay, there's a square root of -3 in that formula because I didn't assume that C is coprime to 3. Soon I'm going to assume that C is coprime to 3, and then you can make a change of variable and it would write nicely. Or nicely, it would write more nicely. But if I want to have a general character, I have to write it like that to be true. Okay, so this is the functional equation that you need. What do you do to compute the one-level density? Everybody starts the same way. You use the explicit formula. So I have a primitive cubic character. I wrote it for cubic of conductor C. I have my phi, which is my Schwarz function, and the Fourier transform as a compact support. So to prove this, you need some compact support. It can be any compact support, but you need a compact support. Then the left-hand side is this count of the low-lying 0, and it's related on the right-hand side to, well, phi out of 0, which will be my main term, and then a sum over prime, where you have the character and, you know, some weight, 1 over square root of num-p, and this would be my error term, presumably. So you see that in my sum over prime, I have my phi app. So I will be able only to bound that on some condition on phi app. So how do you prove that? Well, the zeros are, of course, every time you have a 0, you get a pole of L prime over L. So you're just integrating L prime over L and use Cauchy's theorem so that each 0 gives a contribution. So that's the left-hand side. And the right-hand side, and now you compute this integral by writing L prime over L. And of course, L prime over L will write as a sum over prime powers. So it's not surprising that you get that result. Okay, I say L prime over L writes as a sum of prime powers. Here I only have prime because I put the prime power in the error term. Okay, and actually here the squares of the prime do not contribute to the main term because we have cubic character. For quadratic character, the squares of the prime will contribute because when you square the prime and the L prime over L, you also square the character. So you don't have any oscillation left. But for cubic, they don't consider. So I already removed the square of the prime in that formula. Okay, so what's the one-level density? That's the average of this count of the low-lying 0. The first formula that I wrote was my definition on the first slide. Now I replace this count of the low-lying 0 by the explicit formula of the previous slide. So if you remember of the explicit formula, there was phi out of 0 divided by the log of the norm of the conductor divided by the log x. This is my first term. And of course, asymptotically, this would be phi out of 0. So this is your main term. And then there's an error term. And of course, my S of x, I don't know why it does that. I'm sorry. In the error term, oh, I didn't say my S of x. So my main term is phi out of 0, which, you know, we know phi out of 0 is the answer we want. And with this sum is going to be asymptotically 1. So the main term pops out immediately. So what's happening is I want the error term. And I wrote on the next slide what is S of x. If you remember in the explicit formula, there was a big sum of prime. So this is what is my S of x. So now the game is to show that the main term is smaller than the error term, or S of x is, you know, if you look at this formula, S of x is small o of AW of x log x. And this is where the condition on the compact support will come. So the error term depends on this function that I call S of x. So I don't do all the detail, but if you remember the explicit formula, it's clear what I do. I'm plugging the explicit formula in my average. And so I have an average over the character, and then I have a sum over prime, which comes from my explicit formula, and I flip the sum. Okay, so this is, and all you have to do is evaluate this average over your family of character, or the character evaluated at P for each fixed prime. Of course, we're going to use quadratic reciprocity, or here, cubic reciprocity, I should say. So it's going to be the character at P evaluated at conductor in my family. This is what we want to do. And of course, here we know to know about the family. If the sum over chi is a double sum, clearly it's going to introduce complication. So we just need to show that S of x is small o of a of x log of x, as I said, for maximal support of my Fourier transform, and we'll get our theorem. Okay, and by the way, this is the question that Shasha asked. Okay, what is the support of the Fourier transform? It's staring at you from the explicit formula. So we have phi out of log of np divided by log x. So if the support is limited, that would limit the size of p. So, of course, when you can evaluate those sums, as Kaisa was saying in our talk, well, if the sum becomes too long, there's a problem. So you want to limit the length of the sum, and this is done by the support of the Fourier transform. So the support of phi out is contained in minus VV. So this means, if you look at the formula above, that the log of np divided by log of x is smaller than v, or the norm of p is smaller than x to the v. This is this famous support of the Fourier transform.
Chantal, there's another question. Gergely.
Yes.
Gergely, you wanted to ask a question?
No, that was by accident. Sorry.
Okay, go ahead then, Chantal.
Okay.
Nice lecture, by the way. Hi.
Wait at the end to say that. You're gonna jinx me. Okay. So we want to estimate this blue sum. Okay, I'll continue to say the blue sum. That's the sum over the family. So everything I said before is completely formal. Take known formula, plug thing in that, and now at some point we have to do something. So let's try to do something. Let's try to evaluate that sum. Okay, again, analytic number theory 101, or we evaluate that, use Mellin or Perron. So I wrote, I want to evaluate that sum, so I'm going to integrate the generating series in this expression, so using Mellin inversion. And what is the generating series? Okay, again, at some point I have to do something. What is the generating series? I'm counting character by conductor. So of course the denominator is the norm of the conductor to the s. And the top, well, I'm counting characters. I'm counting every time I have a character, I'm doing chi of p. So the top is the sum over all character in my family with conductor c of chi of p. Okay. Just wrote my generating series. Again, I didn't do anything, so I just keep writing more formal and formal things. So we want now to evaluate this sum over the character of first f3 and then f3 prime. Okay, so we have to understand what are the character in the family f3 and in the family f3 prime. So as I said, what is f3? So the family of all character over q omega. For each prime pi, we have two cubic residue symbol. Sorry, we have two cubic character mod pi, the cubic residue symbol, and here it's canonical, of course, because e to the 2 pi I over 3 is in q omega. So you can say which residue it is mod pi for every pi. So we have this character and its conjugate. Okay, so for each prime, we have two character, chi pi and chi pi bar, which is also chi pi square, or you can also write it as chi pi square, because of course you define the character at conductor by multiplying those together. And also we're going to use cubic reciprocity, and then it gets a bit confusing because there's p and pi, I'm sorry. So p is, your prime which shows in your L function. This is the ideal, it's an EKL function. So this is, the script p are summing over your L function, and pi is what I use to build my character. That's summing over my family. Of course, I want to reverse that. I'm doing chi pi of p. I'm going to reverse that by fixing the prime p and putting the pi inside. So what are the primitive character modulo some square free conductor C? Well, they're given by multiplying the primitive character modulo the prime dividing C. And the number of those characters is 2 to the number of divisor of C. Because every time I have a prime, I have a choice between the cubic residue symbol, its conjugate. So if I have 2 primes, for each prime I can make a choice. It means 4th choice, etc. So the number of such character for each conductor is 2 to the number of prime. So what does it mean? It means I can write the generating series like that. Remember, I'm looking for the generating series of chi p of pi, where pi are the conductor of my character. Well, the pi combined to give my conductor of my character. So for each pi, I can choose either chi p or chi p bar, which is what I wrote. So this is exactly my generating series. Okay, this is how the double sum translate. So how to understand, now we need to understand this generating series. So I can write it like that, of course, up to a function hp of s, which is going to be absolutely convergent for a real part of s bigger than 1/2, because the first term is a square in that. Or, I'm going very slow. I can write it like that. Okay, the point is my generating series is the L function at chi p times the L function at chi p bar times something which converge absolutely for a real part of s bigger than 1/2 plus epsilon. Okay, so now I know everything and I can find a one level density. Of course, the L function at the character chi p and chi p bar have analytic continuation to the complex plane, and my function fp and hp, as I said, converge absolutely for a real part of s bigger than 1/2. So back to the Mellon transform. So I want to evaluate the blue sum, which is the sum over character. I wrote it as this Mellon transform, and now I'm going to move the integral to 1/2 plus epsilon. The function fp converges absolutely and uniformly. I don't need to know anything about that. Of course, ls chi p and ls chi p bar converge, but their size depend on p. And this is where you can either use some bound, some subconvexity bound to know their size, or use the Lindelof hypothesis. So Zev was talking about, if I want to do non-GRH bound, this is here, I will do it. And one thing that you would notice is, now I'm doing the Riemann hypothesis. So I move to 1/2 plus epsilon and I use Lindelof. So I have 2 L functions. So when I use Lindelof, it's going to be np to the epsilon times np to the epsilon, which does not change size. But if you don't use the Riemann hypothesis, you have 2 L functions. So it's going to get big fast. So for this family where you have a double sum, the results are really not going to be good. But for Lindelof, well, you can have 2 in a row, it doesn't matter. And then I just finish the argument. This computer doesn't like me. So I just finished the argument. So x to the 1/2 plus epsilon is because I moved the integral. You see x to the s. S is now 1/2 plus epsilon. And p to the 2 epsilon, this is the Lindelof hypothesis. And outside my sum over character, I had a sum over prime. Okay? So now I just evaluate that and I get that the error term is x to the 1/2 plus v over 2, v being the support of my Fourier transform, because as I said, this is what's going to tell me the length of my sum over prime. And you have to beat x. So it's only possible when v is smaller than 1. Okay, and if I took the family f3 prime, by the way, I would do exactly the same argument. And if I use Lindelof, I would get exactly the same thing. I don't have a double sum. I would have only 1 L function, but I would get the same thing for the trivial argument. But now we want to improve that. Okay, the support of phi is...
I'm so sorry, I'm sorry, Chantal. Can I ask another question? So did I miss the place where you use GRH here? Because I mean, on this page, we only needed Lindelof hypothesis.
Yeah. I said GRH, but I mean Lindelof, yeah.
Okay,
yeah.
So Lindelof is enough. Thank you.
I use GRH to say Lindelof is true. Yeah.
Okay, I got it. Thank you.
Okay, the support of phi add is too small to get any result in that case. So, by the way, here I put this parenthesis to say, okay, you're over the full family. What could we do? Is there any other way? Yeah, if okay, I cannot improve -1/2. It doesn't mean that anybody else cannot do it, but it's not in the literature. So what else could you do? You could, of course, compute the moment. You could compute the first moment over the full family, which is not in the literature for number field. And I think it would be under GRH, because I think if you have this double sum, I don't know, you could control the non-principal term. I think it would be under GRH. Well, right now I can do it under GRH, or one of my students can. And you can use a sharp upper bound for the second moment. This you can also do under GRH. And you can get a proportion in the full family F3. using the method of moment. And this will, of course, not give you a positive proportion if you look at it. So don't forget here, this is the family F3. So the sign of the family is x log x. The first moment is x log x. The second moment is x log x times log x, which is x log square x. So you get a constant times x as your proportion, but it's not a positive proportion because the family has size x log x. But this is work in progress of one of my students. You don't get a positive density in F3, but you get this, this number of non-vanishing. So to get a positive density, you would need to get an upper bound for the second modified moment. Okay, the constant C1 squared over C2. Remember, I told you the constant using this technique is crazy, crazy small. So if you want to get a proportion inside the full family F3, well, the proportion inside the family F3 prime is way better. Okay, but this technique you can improve by modifying the moment. Okay, little parenthesis, and now, okay, now I show you F3. Now let's move to F3 prime. How do we improve the support past -1, 1? Again, this is very classical. You use Poisson summation. So I rewrote my S of x, and the change that I have before it was chi belong to F3. Now it's chi belong to F3 prime. Okay? And that's very important because chi belong to F3 prime, well, it's summing over square free element of z omega. Okay, by putting a sieve is the same thing as summing over all element of z omega, and then I can use Poisson on that. Poisson over z omega to transform the sum in another range. But if I have a double sum, it becomes more complicated to do that. Okay, the tint family F3 prime, this is the setup. For each conductor C, there's one character, square free conductor. Because for each prime, you choose the cubic residue symbol. Okay, for each conductor C, a priori, there's 2 to the omega C character, but you pick one by forcing at each prime to get the cubic residue symbol. Okay, by the way, there's always condition of C congruent to 1 mod 9 because we need an Eke character. We need something which is trivial on units. So, I mean, there's a lot of things which are not exactly true, but the paper is on the archive. You can look to get the exact statement. So for this family, for each conductor, I have one character. And then again, the same thing, I use cubic reciprocity to write my chi P, which is now chi C of P as chi P of C. And I can sieve out the condition on C. So I can write my blue sum as a sum C belong to Z omega. And this is the kind of sum that we like because we can use Poisson on those sums. Okay, if I do the F3 sum, that would be, of course, I'm repeating the same thing, and it would be a double sum over C1, C2, and Z omega. Okay, well, provided I also do all the sieve, that would be a double sum on those. Okay, Poisson summation. The Poisson summation for here it's a primitive character. Yeah, Poisson summation over Z omega. This is from a paper of E. Brown in 2000, where he was looking at the average of cubic Gauss sum at prime argument. So on the left-hand side is the sum that I have. I'm summing over all C in my family, chi of C. C is my family of character, but I use cubic reciprocity. That's why now the C is inside. And that's just the sum over Z omega. So using Poisson, I can rewrite it as another sum over Z omega, where the difference is, okay, chi is replaced by chi bar. That's, that's not a big difference. There's a change of scale because before norm of C was smaller than X. And if you look on the right-hand side, the norm of M is smaller than the norm of F over X, if you look inside W at. And also, it's X divided by the Gauss sum. So we're going to have to use the Gauss sum. When we're going to sum that over the prime, it's going to be average of cubic Gauss sum. Okay? In our case, chi is our character chi P, and we have to do a sum over P. Okay, so in that formula, well, omega t is the two-dimensional Fourier transform of your test function. It has the same property. This omega at of this square root you can think of it as the norm of M is smaller than the norm of F over X. That's basically what it tells you. And G of chi is again the Gauss sum that we had before. Okay. So we use Poisson. And now the sum over N, which is the sum over your family of character, you write with Poisson. And then outside there's a sum over P, and we're flipping the sum. And now I'm ignoring a lot of details, and I'm just concentrating on after flipping the sum, what do I have to estimate? So I have chi pi of n bar. This is the character coming from Poisson. And now, a bit perversely, now I wrote p as the ideal generated by pi. So now my pi index my sum over prime, over the prime ideals. Okay, so I have this character at my prime p. I have the Gauss sum, and I wrote the Gauss sum a bit differently because I'm staying away from 3. So I can write my Gauss sum a bit simple by making a change of variable and getting rid of the square root of -3. Okay, and I have, okay, there's some normalization. You evaluate that, and then you have to do a couple of partial summation. So I put norm of pi to the 1/2 in the denominator because that's natural. That's the size of the Gauss sum. There's a lambda of pi, which is just a character of absolutely bounded modulus, because there's a lot of things which are congruent to 1 mod 9 and 1 mod 3. So you need to sieve for that. So that's what the lambda of pi is. So at the end, we have to evaluate those sum where I have the character chi pi, I have a Gauss sum, I have some character lambda, which really is there, but it's not important. It's going to pass happily through every estimate, and it's happily bounded. And I rewrote my Gauss sum in a better way, so they're cleaner. The Gauss sum, or the G1 chi, this is the sum over all alpha mod pi, while you evaluate the character and you multiply by the exponential. And the shifted Gauss sum is the one where you shift the exponential. So G1n is the Gauss sum as before, with a slight change of variable. Gn pi is in the exponential, it's not the trace of alpha over n, it's the trace of n alpha over pi. And what happens is the shifted Gauss sum, when n and pi are coprime, is the character times the Gauss sum. It's very easy, that's a simple change of variable. Okay, so this is at the end of the day, when you do that, what you want to estimate. So you need a good estimate for that. Okay, so what do we expect as estimates for that? There's a lot of estimates on Gauss sum. So the first estimate, notice that my average of Gauss sum, it's over prime. So it's not a sum over all f, but I'm starting with that. What about this one? Just go over all f and z omega, f congruent to 1 mod 3, the norm of f is smaller than x, and you have your Gauss sum, whose an absolute value as size norm of f to the 1/2. But of course, the sign of those Gauss sum is not constant. So what is this sum? This is in a 78 paper of Patterson based on the work of Kubota. And there's a lot of cancellation here. The sign of the Gauss sum oscillate, and actually you get that this sum is x to the 5/6. The trivial bound being x. Okay. So we want to catch some of this oscillation by summing over prime. So what's the proof of that? You have to understand the generating theory, and this is where things get bizarre, because the generating theory associated to Gauss sum, they're not associated to automorphic form. For example, this has no Euler product. This is not multiplicative. So this corresponds to other forms which are called metaplectic form that you have to study to understand this generating series and understand where the generating series has poles. And once you know that, well, you use Perron when you pick the contribution of the pole. So there's a pole at 4/3, and 4/3 minus 1/2 is 5/6, and that's the 5/6 on the top. Okay, because I divide by norm of f to the 1/2. Okay, now what about a prime argument? Again, there's another result in the literature. There's a first result of Edbron and Patterson, which gives a bound at prime argument, and a second result, which is we use a lot in this work, of Edbron in 2000, which says that if you go now at prime argument, g of pi divided by norm of pi to the 1/2, you're going to get also x to the 5/6 plus epsilon. Okay, the difference is you're running over prime argument here. And actually, there's still, oh, I said a word about the proof. So you have to, again, those are not multiplicative. So how do you go from the full sum to the sum over prime? You use Von's identity to decompose the sum over type 1 and type 2 sum. That's the proof of Patterson and Edbron, refined by Edbron. And then you bound those type 1 and type 2 sum using the work of Patterson for the type 1 and mean value estimate and the cubic large sieve developed by Edbron for the type 2. And there's still an open conjecture if you want to work on that. So, okay, this is bounded by x to the 5/6 plus epsilon, but the conjecture is that when you run over prime argument, this should be x to the 5/6 over log x with an explicit constant. So this result of Edbron just falls short of proving the conjecture. Okay, so this is basically the core of our paper, and I'm not going to go into that. So we have to evaluate this sum in our case, which is not Gauss sum, but some kind of shifted Gauss sum because we have a character. So this is what we prove in our paper. You go to sum for pi congruent to 1/3 norm of pi smaller than x, this average of Gauss sum that I said that we have. And the equality on the first line is just a rewriting. Okay, so our rewriting as an average of shifted Gauss sum, which is actually something which is treated in the work of Patterson, except now there's a condition between pi of n, which is, you have kind of to do some work to remove it, but it was done in other paper, for example, in Bayer and Young, it was not exactly like that, but some similar computation. So what you do is you take the object that you have and you write it in terms of the functions that the generating function that were studied by Patterson and of which you know the property. And you remember the result of Edron and Patterson was x to the 5, 6, and the result that we get here is that. So the important thing is you want to keep the dependence on m, because the dependence on m will go in the other sum, and that's why we don't get 6, 5. That's why we get 13/11. It would be natural to think, oh, we're going to get 6/5 because of that result. But of course, you have to keep the dependence on m, which is which is the sum over your character. You have, after Perron, you got a sum over m, and you have to keep this dependence in the next sum, and that's why it's going to give you the 13/5, 13/11. Okay, so all the other terms are there, but they don't count. At the end, the term that gives the most is the x to the 5, 6 norm of n to the 112. Okay, that's the main result that we prove using those, the previous work of Edron and Patterson. And then you put back in S6, if you remember. So this is the sum over n. Now you have a sum norm of pi smaller than x. Well, in fact, it's norm of pi smaller than x to the v. And then you're going to get that you can bound the error term provided that v is smaller than 13/11. Okay, the v will come because after you do this estimate, now you have to sum, and the length is norm of pi is smaller than x to the v. Okay, I don't want to go into the details of that. I just wanted to explain what is the difference because this estimate that we get and the previous estimate, and it's basically that you have to keep the dependence on an extra parameter and of course redo the argument, and sometimes they're different, and get that you can push to the next sum and get an improvement. Okay, that's all I wanted to say. Oh, I'm sorry. I don't know why there's this scribble on my that's all I wanted to say, but this is how you show the result. So you can compare. So this is the one for the family F3 prime, where you get minus 13/11, and this gives you, as I said, a proportion of non-vanishing, which is 2/13. Okay. So first I did you F3, you get minus 1, 1, and then for F3 prime, you can use Poisson and do those estimates on Gauss sum, and then you get this result. And that's the end of my talk.
Okay, thank you, Chantal. If there are any questions, comments, this is a good time to ask them. Chacha, you had something else you wanted to ask?
Yes, I do. So, okay, so basically you don't really need GRH, but you only need to bound the size of L on the critical line, and that's where you use this Lindelof hypothesis.
I'm trying to. We use I know we use Lindelof, of course. So, but I'm trying to think if we use GRH really. I would say no, but yeah, maybe some other result that we use. Yeah, but yeah. We also have a result.
In case you
Lindelof by the appropriate bound, and we record the result. But I think we only use Lindelof.
Okay, so so in that case, do you really need the bound to be t to the epsilon? So I mean, will any bound, like certain bound, this L works actually? So something weaker than Lindelof. So if you just assume a certain bound on L works.
But what we do is we prove a non-conditional result using the best, bound which is known, and then we use Lindelof.
Yes. Okay, I see.
you can say, well, if I have something else in the middle, a quasi, I know there's something like a quasi-Riemann hypothesis. I don't think there's a.
Nice. Thank you, and that was very interesting.
It's so nice to see you.
Yeah, very nice to see you here.
Good. Anyone else?
May I ask a question?
Yes, Rudil, go ahead.
So conjecturally, do you expect the L of half chi strictly greater than 0?
I'm sorry, do I expect what?
L of half chi strictly greater than 0?
No, it's a complex number there, huh? Because the character takes complex value.
I see. But for certain class of character, can it be?
When you do the first moment without absolute value, even if the value are complex, the moment is real because chi and chi bar show. So the sum is real. But I don't know if it's a. I mean, the constant is a real positive number, but I don't know if you do L1 half chi plus L1 half chi bar, it would be real. But I didn't think about it as positive or negative.
Yeah, so I was just wondering that for a very certain class of character from your method, it's possible to push to show strictly greater than 0 L of half chi.
Yeah, here it's a complex number, so that's why the question is.
Yeah, it's not like quadratic characters where the central value is a real number. It's a complex number, so you can't say.
If you do L1 half chi plus L1 half chi bar, it would be real. So maybe you can ask about that one.
Yeah. Thanks a lot.
Okay, anyone else? All right, so thank you, Chantal.
Thank you.
So we can be civilized and have a few-minute break until the next talk, which is in 7 minutes. Peter is here already. So while everyone is getting the coffee, Peter can practice sharing his screen. Peter, are you here?
Yeah, thanks. Great talk. Thanks. Let me show my face. Okay.
Yeah, now we saw your face. We saw your face already.
I was just checking. No, I exist. All right. So I need to share screen.
Hi, Professor Rock.
Hi, how are you?
Hi.
Happy birthday.
Thank you.
Yeah, now call me Peter. Come on, man. I enjoyed very much the on Monday all the things that were said about you. Fantastic. I didn't know about Sound, that he used to come to your house regularly. Just let me try get this thing working. It's a bit of a problem. All right, you guys see that?
Okay. Yeah.
Okay, let me wait. I can fix this up a bit.
Perfect.
Single page. All right. Okay, so then
yeah, we're all getting pretty good at this.
No, I'm not. I don't know what the hell I'm doing. It's kind of frightening. But yeah.
Well, I remember when you asked me to teach you Google, so I think you went a long way.
Yeah, I remember you said that. I remember you said, "Don't give me."
Maybe that means I'm old, but I remember that.
I remember when you said you're collecting the papers on a computer. I said, no, that's because you were ahead of the curve. Let's put it that way. But by now, I'm sure you're behind.
Yeah, I have 15K documents on my computer.
Okay.
I mean, in mathematics.
Okay.
I also have some secret stuff I'm not supposed to talk about here.
Yeah, that's the danger with this sort of thing. It might turn up when you're playing. You're gonna share screen. You don't know what's going to come up here.
Yeah.
Okay, so we got a few more minutes.
No, but you have a huge office with all these cabinets, so there you can store your papers in
No,
physical
but I haven't
form.
been. I haven't been. Actually, I went to my institute office for the first time in about a year, 8 months yesterday, because there was a celebration for Vigdis and Lovas, but Vigdis. And so we actually had a hybrid in-person 8 people in the room meeting. I'll be back in a second.
Yeah, did you guys have
such
a
beautiful
celebration?
handwriting?
Did you guys have a celebration for Lovash, Georgi?
Well, actually, you say Lovas, S and Z, that counts as one letter, S in Hungarian. So it's not like Erdős, which doesn't have the Z. Lovas has the Z. So no, we had no celebration yet. So
Okay.
I'm sure we'll have something. I guess he's busy now.
Well, maybe when it's possible to have physical celebrations. Hopefully it'll be soon.
Yeah. It's recording, so I have to watch carefully what I say. I wanted to say something about politics, but
Oh, no, don't do this. They're listening. They're listening.
I will save that.
They're listening to you. We actually have elections coming up in a few days. So.
Oh, so that's why you got the shots. Okay, now I understand.
Of course. No, the shots are independent, but that's why restaurants are open.
Are you sure?
Right.
You never know these.
Yeah, you never know. You never know.
I just watched a documentary on AI. First on AlphaGo and then on AI, and now I see the word differently.
Yeah. It's no longer a paradise, right?
So Peter, we just praised your handwriting.
You what?
We praised your handwriting.
Yeah, you like it?
Yeah.
Okay, thank you.
Yeah, we like it.
All right. Well, I'm forced to, well, the way I do it is I don't use an iPad, although I've started to do that as well, but that's horrible. I have a scanning machine. It's the most important thing I've had for years. So
it's called a phone nowadays, a scanning machine.
No, you can't scan. I can't scan on my phone. Like
some people can.
You mean you take a picture?
No, you scan.
You scan? Oh, wow.
Yeah. It's called an iPad.
Technically, it's taking a picture, but then there is AI in the background. AI makes it a scan.
Yeah.
Maybe I should see how to do that. Well, anyway, the iPad is, of course, what everybody's using. And there I found it very difficult to write. I mean, my handwriting on the blackboard's no good either, but it's even worse on there. Some people have quite beautiful handwritings on the iPad. Yeah. And I'm talking about real handwriting, not canned stuff.
Yeah, it's a matter of practice. So Noli, do we want you want to switch on the recording?
Sure.
Yep. Now it's on. Now it's on. Okay, very good. So I think we can start. So we're happy to have Peter Sarnak all the way from Princeton early in the morning, and he'll tell us about Plancherel measure and Hecke eigenvalues. Go ahead, Peter.
Thank you very much. It's a great pleasure to be part of this great celebration of Balasubramanian. I know Bala, I've met him on a few occasions, but I certainly don't know him the way many of the other participants know him by visiting him for long periods and working with him. However, I've studied some of his papers, and I will start maybe with one of his papers with Ramachandran. But before I start, everything I discuss here that's new is joint with Evita Nestoridi, who's a faculty member here at Princeton and a former student of Percy Diaconis. So you can see the word cutoff, and I'll get back to that. That is one of her primary interests. And Nina Zubrilina, who's a second-year graduate student here. And let me also make clear that this is work in progress, so maybe theorems with a little t, they're being written up, and any mistakes that anybody can point to are go on my head and not on theirs. All right, so let me start. So there's this, you don't see anything obscuring anything, right? For me, it's the, I don't know why it's obscuring. It's clean for you.
The common thing, the
looks
bar
great.
obscures our screen is fine. Our screen is
Okay.
It looks great here.
All right, okay. So I want to start with a paper of Bala and Ramachandra from 1976, which with a beautiful title of The Place of an Identity of Ramanujan in Prime Number Theory. This is a paper which has only 2 math reviews, and it's an extremely important paper, as I want to explain to you right now. And I'll go through a little bit in the history. So in this paper, they show how to incorporate some elementary upper bound sieve theory to give a standard zero-free region. Now, by standard, I mean here logarithm types. I'm not interested in the powers of logarithm. Of course, there's the work of Vinogradov, which gives logs to fractional powers. Those, of course, for zeta are remarkable achievements. They're not so useful. The main standard zero-free region, I mean the method of Adamar de la Vallée-Poussin, which gives a kind of logarithm versus a power or ineffective zero-free region. And they discuss how you can get this from an identity of Ramanujan, which is in the simplest version being the one I'm writing down here. I think it was Ingham who first noted that this Ramanujan identity, together with the simple lemma about positive coefficient Dirichlet series, gives you a one-line proof of the prime number theorem. But it gives a poor lower bound for L1 plus IT, something like t to the minus a half as t climbs up the line 1. And what they observe is that you can recover essentially the best, or let's say just a standard zero-free region, by using some very elementary upper bound sieves, which are elementary but very useful, by estimating this quantity sigma IT at primes, and then showing that for most primes, this quantity has to be quite big. So I'll call it a sieve bootstrap. And it's that rather than Ramanujan's identity that I think has a fundamental place in the theory of numbers, as I'll explain now. Now, there may not be that many references to this paper in MathSciNet, which is, I think, everybody's standard today. But if you make it into Titchmarsh's book on the zeta function, then you've done something that's actually of substance. And Heath Brown, in his updated comments to Titchmarsh's book on zeta, points to their paper as a means to recover without the usual trigonometric polynomials, which produce more zeros than poles and give you a standard zero-free region. He points to their paper as a very novel and interesting idea. He also points to another proof of the non-vanishing of the zeta function on the line 1 using Eisenstein series. In fact, he adds quite a lot to the book in another chapter in order to give this proof, which is a spectral proof, differential equation proof, and in my view, the most important proof that exists for the reasons I'm about to give you right now. On the other hand, he says the region, the lower bound given by the spectral or by this Eisenstein proof gives a very poor zero-free region. And I have a paper in which I'll return to in a second, show that actually the bootstrap argument of Bala and Ramachandra allows you to bootstrap the Eisenstein proof to also get a zero-free region, which is standard. And so it doesn't give you something that's bad. Actually, it gives you something good. But as long as you add this sieve argument, this elementary sieve argument. So to my view, that's very important, and so important that let me point the following out. So in the context of automorphic L functions, the Eisenstein series coupled with this bootstrap is in fact the most powerful method known to mankind today to prove non-vanishing on the line one. It works in situations where Adamard and de la Vallée-Poussin can't possibly work, because you're proving non-vanishing on the line one when you don't even know that the Euler product converges near the line one. It only converges for real part of S bigger than 3/2. This is a temporary holdup in the sense that if you knew Langland's functoriality, you would be able to reduce all the problems to what are called standard L functions. And then maybe this would be less relevant, but that's far off. And you could argue that all these things in an ideal world would be gone once somebody understands the Riemann hypothesis. So I'm talking about present day technology. And from that point of view, this proof coupled with this bootstrap gives all, especially in the T aspect, gives the best known and every known case, and cases that Adamard and de la Vallée-Poussin can't arrange, because you can't concoct the right L functions, the right combination of L functions to produce more zeros than poles as they invented. So you'll find this discussed in a paper of mine. And then Gelbart and Lapid carried this out for the general situation in the Langland-Shahidi method. Goldfield and Lee looked at a very interesting problem. So let me just end with that case. That is the Rankin-Selberg L function, and Humphreys actually used the sieve method more efficiently to show that this Bala-Ramachandra method actually gives you a standard zero-free region for all Rankin-Selberg L functions on GLN. And it's a misunderstanding that without that, you can't deal with all cases, in particular if pi and pi primed are not one of them self-dual. And we don't know how to concoct the functions in our present understanding, but this method of Bala works. So Bala, if I give you the following, today, your method, I would say, is the best we know towards the Riemann hypothesis. When I talk about the Riemann hypothesis, I mean the grand Riemann hypothesis for all automorphic L functions.
Thank you. Thank you.
So I love that paper. It's a great paper, and it's a place. The method has a place in the theory of L functions, not for Dirichlet L functions as much, where other methods have been slightly stronger, but in generality. All right. I will now turn to the topic of my talk, which is concerning bounding the size of spaces of automorphic forms, and then an application. And it's the application that the three of us have been looking at. In a paper a long time ago, in 1984, when I was mainly interested only in mass forms, I only formulated this and proved it for mass forms. I proved the following theorem, that if you take all Hecker mass forms for the full modular group SL2Z, and you order these forms by their Archimedean eigenvalue, by their Laplace eigenvalue, so that's how you order them, it's their conductor. And you form the numbers lambda fp, which is 2 cosines. So you define theta fp by this relation. And if the Ramanujan conjecture is true for mass forms, which we still don't know, then these thetas are between 0 and pi, but otherwise they could be off 0 and pi. The lambdas, of course, are between, there are bounds which are quite strong. The theorem that I was interested in then was that if you look at this infinite vector, so for each f, you have an infinite vector of numbers, which are the second eigenvalue, the third eigenvalue, the fifth eigenvalue, the pth eigenvalue for each prime p. It's in this infinite product space. And as you order the f's with respect to their size, this becomes equidistributed with respect to a very important measure. In this case, it's a product measure. It's a product of p-adic Plancherel measures, as in the title of this talk, which are exactly these measures. So they are supported on 0 pi. There are a few things I want to point out about it, but these become equidistributed with respect to that. And the proof uses the Selberg trace formula for SL2Z and traces of Hecker operators. There are two things I want to point out about these measures. The first is that these p-adic Plancherel measures for each prime p vanish at 0 and pi. So the sine squared theta vanishes at 0 and pi, and this will be critical to the highlight of this lecture, is exactly that vanishing. And the second thing is, as p goes to infinity, this measure converges to another measure, which is very important, called the Sato-Tate measure. So these are 2 points I wanted to point out, and this is a general fact. All right. In 93, and I'll tell you a story about this in a moment. Sir, I first learned of this. He was giving a lecture here, a colloquium here in Princeton. I think Zeb was probably also in the audience. Proved the following theorem. It's the same theorem, but just for Hecker eigenvalues of holomorphic forms of even integral weight for gamma naught n, so not full level, but we're letting the n go to infinity. He fixed p, he let n go to infinity. He also allowed the weight to go infinity, but his primary interest was n going to infinity. This is by far the most interesting case of, you'll see in a second why. Again, he puts lambda fp, the Ramanujan conjecture asserts that this ratio is at most 2. So you write it now uniquely as 2 cosine theta fp, and now theta fp is a number between 0 and 1. It's the angle. And his theorem is that as n goes to infinity, these eigenvalues become equidistributed with respect to the Piatic-Plancherel measure. I should have said that the Piatic-Plancherel measure, one more thing about it, is comes very naturally from the trace formula. It's the contribution to the trace formula of the identity conjugacy class as computed by Harishchandra in quite great generality. So that's completely natural from every point of view. Now what's happened? I've lost my screen. You see me?
We see you. You're now back to the slide about mass forms.
Your share screen is paused. So how do I undo that? Resume share. Okay, thank you. Resume share. I don't know. There's something called CrowdStrike comes and strikes me every now and then. I don't know what it is. It's probably some bug I've got. All right. So it's a contribution from the identity conjugacy class. And the other thing that will be important for later is it's also on the p+1 regular tree, the random walk return Keston measure. They're all the same thing. All right, so Serre proves this theorem, which is the same theorem, and he fixed 1 prime. And his interest was k equals 2, holomorphic forms of weight 2, because he was very interested in the modular curve x naught n, its Jacobian, and its behavior as to how decomposed as isogenies, up to isogeny as a product. And you'll see why in a second. So he fixes a number d, an integer d, and he defines all the modular forms. So these are Hecker eigenforms for level n, weight 2, and this d is fixed, for which the lambdas, the actual eigenvalues, are in a field. They'll always be in a totally real field in the way of normalized things here. I'm looking, there's no central character. Totally real field of degree at most d. So for example, if d is 1, we're looking at all the modular forms whose coefficients are integers. If d is 2, they lie in a quadratic extension. And in general, by the work of Shimura, there's a Galois orbit. There are these, the forms break up into Galois orbits depending on how their coefficients, where they lie. And that is how the Jacobian decomposes, and how that behaves is quite mysterious. So as I said, if d is 1, this is just all the modular forms whose coefficients are integers. And at that point, this was 1993, I was sitting next to Andrew Wiles in the lecture. Wiles had already told me he thought he could prove the Shimura-Taniyama conjecture. And Serre was wondering aloud whether there are enough modular forms to accommodate the conjecture. He said, are there enough modular forms with integer coefficients on level n? So maybe there aren't enough to accommodate all elliptic curves. Of course, Andrew, if any of you know him, just sat there quietly and silently, didn't say a word. So this was his interest. And of course, since then, Wiles didn't prove that theorem. And these S2D with these 1 would just be all elliptic curve modular forms. And he's asking to bound that number. Wiles showed us that there are enough of those, remarkably proved it. The number of elliptic curves with conductor n has a non-trivial bound, and which is much smaller than n. So the fact is there's ample room here. And in fact, one can even improve that exponent a little bit. This was done by Lillian Pierce and Helfgott and Venkatesh sort of simultaneously. So that case we understand. But Serre did something rather interesting with his equidistribution theorem. He proved that for any fixed d, and when d is large, we don't know much about this decomposition, that the number of modular forms whose coefficients lie in fields of degree at most d is little o of the total number. It's just a modest improvement, but that's what he was after. And he asked if you can get an exponent here. In other words, a power saving. And I'll return to that. So that was Serre's interest, and it was a very clever use of this equidistribution that he proved. Rammurti and Sinha in 2007 worked quite hard to, not giving the dependence on D. They gave explicit dependence on D here, which requires going through Serre's argument and counting number fields with certain properties, and that bound depends very poorly on D. But they, instead of getting little o, are able to put a log there, small step towards Serre's question. And that also allows you to identify all x naught n's which have only integer coefficients, meaning they decompose into products of elliptic curves, like the generalization of x naught 11, which is an elliptic curve. All right, so Serre's was interested in that, and I'll return to that in a minute. I want to point out there's some improvements or results which are rather pretty, which do get power savings or even more. So the case of weight 1 is very different. So if you take weight 1 holomorphic forms, which are holomorphic, then there's a well-known theorem of Deligne and Serre that there's a 1-1 correspondence with these. I allow a quadratic central character. There's a 1-1 correspondence between these and finite, I emphasize, finite two-dimensional irreducible Galois representation. Now, the finite subgroups of GL2C are very, the Platonic solid groups and some simple CM guys. So we understand them very well, and the traces of those, which will then be the coefficients, are then going to lie in a finite set. And one can exploit that to actually get a power saving. This was first done in a beautiful paper by Duke. He uses the Peterson formula in an undual form, and it was improved a little bit later by Michel and Venkatesh. I have a nice story about that too. Venkatesh was I don't know, maybe a second-year graduate student here in Princeton, and he came into my office pointing out that he could improve on Duke's theorem. And I got, on the very same day, an email from Michel with the exact same improvement. So I thought, well, okay, I must do the obvious thing here, is they must write a joint paper, which they did, and that's their paper, and it was the beginning of a long, beautiful collaboration. So one can get a power saving for weight 1, but the reason is because the coefficients, the lambda fn's, are in a finite set, period, as opposed to what's happening in weight 2. All right, on the other hand, there is some very beautiful breakthrough recently in the K aspect, and the K aspect is very different, and it's quite natural that one should be using the R equals T methods of Wiles and Taylor to attack this problem, the Galois deformations, which actually were the methods that allowed you to prove the Shimura-Taniyama conjecture, as you know. And last year, Caligari and Sardari proved the following beautiful theorem, that if you fix P, the condition on P is just technical. If you fix P greater than or equal to 5 and you look at Hecker eigenforms of weight, even weight K, and you ask about the multiplicity, in other words, how many of these have their coefficient equal to 0? They have some other results about not 0, but equal to 0, which is the most interesting. And they show they're only finitely many. That's quite beautiful. That's as strong as anything can be. Only finitely many holomorphic forms of. So the K aspect is very different, and the proofs use the full force of the interpretation in terms of Galois representations. On the other hand, these methods so far have not worked in the n aspect. Whenever you prove a R equals T theorem, you might say you're counting some other objects, but those other objects, nobody knows how to count. The elliptic curves with conductor n, one can make some estimates. All right, so I'll now state the first. Now, this is a little t. I'm following a tradition of Mumford. Little t means being written up. Little theorem 1 of the three of us. Fix a number less than 2. And that number is going to be fixed. And that it can be as close to 2 as I like is important. Choose any. Now, the number that's going to go to infinity is capital N. We've only worked this out so far for n prime, but that doesn't matter. It's going to get more complicated in general. Suppose you have r primes that do not divide n. That's a misprint there. And I've got degrees or integers, L1 for each r, and such that L1 log P1 plus LRPR is less than or equal to this constant, which is less than 2 times log n. And form any polynomial in R variables in cosine theta of degree L1 in the first variable and L2 in the second variable up to LR in the rth variable. Then if you take 1 over the cardinality of the number of elements in S2n, I should have said that in weight 1, the Duke work is about the dimension of the space of weight 1 forms. That doesn't, Riemann-Roch doesn't give you that dimension. Of course, we know the dimension here of S2n by Riemann-Roch. So 1 over the number of forms, f in S2n of this square of this polynomial whose degrees are allowed to be that big, and you let n go to infinity, and that will converge. So this is a quantitative version, and I'll say a few words about it. Quantitative version of this convergence theorem that I mentioned at the beginning. That will converge to, so it's 1 plus little o1 times the integral against the product Plancherel measures of the same function. And the important thing here is that the polynomials are allowed to have arbitrary coefficients. I'm allowed to choose p. The only condition is on the degrees, so that I can play a game and choose very optimal p's in several variables here. Okay, so that's the theorem. Let me say a few words. So the quantitative has a twofold significance. The flexibility in several variables, which nobody seems to have exploited before, but we're going to do it now. So the degrees, I just said this, the degrees, the only thing that's limited is the degrees, but not the coefficient. So it's really a bilinear inequality built in with these polynomials in several variables. The second comment I want to make is the restriction on the degrees, I repeat it, to allow C as close to 2 will be crucial in the application to non-backtracking. All right, let me say a word about methodology here. So if you use only the trace formula, that's what I had used, that's what Sarah used, that's what Ramurti and his co-author were using, then, and you just use, you can use the trace formula and then you can try work much harder, but what happens when you use the trace formula? You get class numbers of quadratic orders. And if you just put bounds, they sharp bounds, but you forego cancellation. If you just put bounds for class numbers, you can achieve the above. And if you work quite hard with C less than 1, but not equal to 1. You could try work much harder and then take the trace formula and take the class number and write it down in terms of a short Dirichlet series, because it's a L value at 1, switch orders and work galore. You'll land up with Klosterman sums whether you like it or not. So it makes much more sense to do this step immediately and go and allow Klosterman sums. But that means instead of taking this sum with weight 1, you put a weight here which has got a symmetric square L function. Experts are all familiar with this. And then you get a sum which has actually a different answer on the right-hand side, completely different answer. You don't, instead of getting the product of the Plancherel measures, you get a product of the Sato-Tate measures. So it's a subtle change, but it's a change that we've faced over the years. And that's the way we'll go. It's easier because you get the Klosterman sums directly. The use of this and the removal of weights is explained in, was carried out in detail in a paper of Ivanic, Lo, and myself about low-lying zeros connected with what Chantal was talking about. And we do this in general, and we remove the weights there, assuming the Riemann hypothesis, because throughout the paper, we're assuming the Riemann hypothesis. So you have to remove the weights without assuming the Riemann hypothesis. And this can be done, and I think it's first explained, I'll explain right now. But before I do that, I want to say this is a remarkable idea. You actually want to write the trace formula down. You don't want those weights. So the idea of bringing in the weights and then removing them in order to get Klosterman sums, which give you cancellation that you don't see that easily otherwise, goes back, I think, first to a beautiful paper of Henrik Ivanic, where he improves the remainder term in the prime geodesic theorem precisely by this tool. For the purpose of this multiplicity, I have a letter to Rudwig. You can find it out. You would find it on the IAS website, where I explain that you can double a range, you can halve the constant in a multiplicity, you can work very hard to get square root extra cancellation to replace a number which is terrible by half that number, a completely disappointing application. But the double of the range is entirely this lecture for part 2. All right, so now I'll give you corollaries. So firstly, we can do much better on Sarah's theorem, question. We can give a bound of the cardinality divided by log n to any power, but we don't get Sn to a power less than 1. That I don't see how to do, but this is much stronger than just log n. And the proof from the main theorem follows from Sarah's insight that if you fix D, if you fix the number fields in which the Fourier coefficients are going to lie, and you fix a finite number of primes, then because all the numbers and all their Galois conjugates are also going to satisfy the bounds, you'll only have finitely, the number that, this number will depend terribly on D and P1 to PR, but eventually you write down a finite number of polynomials with integer coefficients whose roots contain all the possible eigenvalues, and then you get to, so you fix the P's and the D. So by the way, this notation here means you first fix A arbitrarily large, and then the constant depends on A, as you know. So you fix those, you get a finite number of values, and then you want to actually give an upper bound for the number of F's, which in the torus, so I have R dimensional space. That's how we gain the A here. In the R dimensional space, we can come back here and then optimize our choice of the polynomial. So we make a polynomial in several variables which has its mean with respect to the Plancherel measures small, but its value large at the exact points you want to give a bound, and that way you can get log to any power. And the second corollary that I'm going to use before I change to a different, as in Monty Python, something completely different, is this fact that just for one prime, and I'll be only using this for one prime, and this is where it's very important that we can allow C to go bigger than 1. The fact that we can get as far as 2 is nice, but this particular application just demands that you go over the threshold of 1. And so if I have a sum 1 over the cardinality of the number of forms of weight 2, holomorphic cusp forms, and I sum over those a polynomial of degree at most C times log n to the base P. So that the condition on the degrees of the polynomials, if there's just one, becomes this. And it's asymptotic to the integral of P against the Plancherel measure. Okay, so that's the first half of my lecture. Any questions? Let me say a word here. I've now given a few of these lectures. It's completely nuts. You don't know if people are actually sleeping or listening to you. Zev will interrupt if he wants to, I know that, but let me invite anybody else to interrupt. And if you have a chat, then Zev will just put you in charge of.
Okay, just a trivial question for the mood. So the OR depends on the A, right?
Sorry, which?
The number of primes you play with, that depends.
Yeah, of course, yeah.
You want to
make
achieve.
A, yeah, exactly. R is A, basically, yeah.
Okay, silly question. How does it depend, the OR on A? So how many primes do you need to
No,
take?
it's the same. It's the same. It's the same. It's the same. The
Okay,
constant
good.
is what's terrible. Yeah, that's
Okay.
exactly.
Okay, just
So,
for the
no,
mood,
if you
I
just
know
use-
you like questions. You don't like
Yeah, I know. If you
questionless
just use
audience.
one prime, if you just use one prime, you'll recover Murty. If
Sir,
you use
or the
primes-
Murty.
Yeah, Murty is the one who put the log there. Yeah, exactly.
Okay.
But
Good.
you can see that this is somewhere between weight 1 and weight 2, because in weight 1, you don't have to worry about the primes because all the numbers are in a finite set for all primes. So you can use a large sieve directly and it's much, much easier. But here we actually have to interpolate and make a polynomial large at a point. And yeah, okay. The answer is A equals R. Sorry, I should have said that. All right, now for something completely different, unless there's another question.
Yeah. So if you could get C up to infinity, would it give you a power saving?
No, so the dependence in D is so, the power saving for fixed D. Yeah, okay,
So right now C is 2.
Yeah, right. C is at most 2. Yeah, I don't know exactly. The answers I don't know. Okay, good questions. I don't. All right, so we're going to do something that I've always wondered what Percy Diaconis does and why it's so exciting. And now I'm kind of I'm bored into it. And this is the following. Suppose you go and ask how many shuffles in a casino do they do before they stop shuffling? And it turns out exactly 7. And that's because if you shuffle 6 times, it's not, the deck won't be random. And if once it's 7, it's pretty much random. And if you shuffle 1 more time, it'll be really random. And this phenomenon is called sharp bounded cutoff. And there aren't many cases where it's known. And it's known for the symmetric group with the riffle shuffle, for example. But we're going to be looking at a somewhat different setting. And there's a lot of literature around this. And it's a big subject about sharp cutoffs for random walks. And as you can guess, I'll be interested in the case of a Ramanujan graph where what is the sharp cutoff, bounded cutoff. So we'll be looking at so we'll do combinatorics for a little while, yeah? So X is a connected D regular graph. For us, D will always be P plus 1. You can assume P is not a prime. The only cases where we know these graphs exist are of the form prime power plus 1, because I'm going to make a non-bipartite Ramanujan graph, and the work of Spielman, Srivastava, and Marcus, which produce only bipartite Ramanujan graphs. So, so far we only know how to make these graphs in the number theoretic case, but the discussion makes sense anyway. So let me start without Ramanujan graphs. We have these graphs, they are connected. D is fixed. I'm interested in D's 3, say, and the number of vertices is going to infinity. And this non-backtracking random walk, a lot of words there, is the following. We start on our graph, we start at a point X, and we move at the beginning to one of its D neighbors, P plus 1 neighbors, at random with equal probability. And then we do something which is clever, I think. Instead of allowing myself to walk where I just came from, which is clearly a waste of time if I want to equidistribute quickly, we do this non-backtracking. We don't go back to where we just came from. We have to remember where we came from, and then we move to one of the P neighbors from that step on, and then we make T steps, and after T steps, we'll be somewhere, and we'll have a probability distribution over the vertices of where we are, and there will be a starting point, so things will depend on the starting point. So after T steps, no matter what I do, the number of points, the number of vertices I land up at, if I count with multiplicity, is simply P plus 1 for the first, and then P to the T minus 1. So this number N is extremely important. It's a number of endpoints with multiplicity that I land up at. All right, so the question that has evolved in this community of non-backtracking sharp cutoff is how quickly do we become equidistributed? And how do you measure whether you're close to uniform? So let PTXY be the probability of landing at Y after T steps starting at X. So this is some counting that we're going to do spectrally eventually, of course. And the measure of closeness that is introduced by these early works and seems to have stuck throughout the theory as the most natural is the total variation, which we divide by half here to make a number between 0 and 1. So you see, if I start at x and n is very large, my probability distribution is just a delta mass at the origin, at x. On the other hand, what I'm aiming for is the uniform distribution, 1 over the number of vertices. That's the steady state. And we're asking how close are we to that? And we make this total variation distance. And to begin with, we'll be very close to 1. I've divided by 2 here because I'll just be a delta function at 1 point, and so I'll be completely off at that 1 point and completely off at all the other points. And so there would be 2 divided by 2, it'll be 1. And what happens is that for a long time, you can't be anything but 1. And then what we're looking for is there's going to be a moment at which it'll start to drop. And then does it drop very rapidly? And that's this question of cutoff and sharp cutoff. And what is that cutoff time? And what is the window of the cutoff? So the most important number we define to measure this is the number t, which is the number of steps, the minimum number of steps before the maximum total variation. So we allow ourselves to start at any x. So if you're shuffling decks, you don't know, the deck will be given to you in some position, and then you're going to shuffle and get from any starting point. So the maximum over x, and you want this t to be less than eta. And the question is, what does this function t of eta look like? So as I was saying, to begin with, it's going to be very close to 1, and then we're going to be interested when t gets close to 0. Now, a very simple combinatorial thing here, which is extremely important for us, because we're going to see absolutely optimal sharp cutoff, completely optimal. So if the number of endpoints we can arrive at is less than the total number of vertices, we haven't got a chance to be equidistributed. No matter how, got nothing to do with the random walk, nothing random. So you can compute the total variation, and it's simply the ratio of the number of unoccupied vertices starting from x divided by n. So if at time 1 or 0, you're on 1 point, so this is basically going to be n over n, and the total variation is 1. And then just because you can only visit each guy at, if you were lucky enough that you visited each guy exactly once, the total variation will be, starting at any x, will be 1 minus this number n over n. So it shows that if n, which remember was p plus 1 times p to the t minus 1, if that's less than n, we can't even start to ask for the total variation to start dropping away from 1. That's an absolute combinatorial limit. So if you actually compute what that means, is you'll find that the time to get to 1 minus epsilon, just to drop from 1, is going to be at least log to the base p of n. This is the most important number. This is the cutoff time, because that's the number related to capital N that I just described, minus log 1 epsilon inverse. So if epsilon here is very small, so you near 1, you have, so to begin with, you'll be at 1. I'll show you a picture in a minute. And then you're going to start to drop. You can only start to drop at log n to the base p. Okay, so there are the decisive theorems that were proved a few years ago on this problem after a lot of work. They were interested not only in this non-backtracking. In fact, they were interested in the standard or simple, as they call it, random walk, where the random walker goes back to where they came from, and then they, of course, equidistribute slower, and this cutoff is not as pleasant, but it's statistically interesting. But I'm only interested in the non-backtracking random walk. And for that, they show a remarkable theorem that if you take a random p plus 1 regular graph, so n is going to infinity, you choose the graph at random by a standard model of random graph theory, then the cutoff time, this t epsilon, so the t1 minus epsilon is never going to be, so this number log pn is where things start to happen. And if you want to get this to be the probability, the total variation to be less than epsilon, you're going to take at most log, the same log p, plus 3 times log 1 over epsilon. So there's a log of epsilon inverse, here's a log of, that's a lower bound, that's an upper bound. So what you have is that log to the base p of n is the cutoff time, and the window for the cutoff is bounded, just like I was telling you with the deck of cards. 6, you're not quite. 7, you're good. 8, you're already wasting your time. So very sharp cutoff, and this is called the bounded window cutoff, and it's remarkable that the random d-regular graph as n goes to infinity satisfies this with a bounded window. Okay, we're not going to look at random graphs. We want to look at Ramanujan graphs. I remind you, a Ramanujan graph is a graph which is a d-regular graph. D is p plus 1. The eigenvalue, the biggest eigenvalue, the constant function gives you the eigenvalue p plus 1. And we assume that all the other eigenvalues are less than 2 root p, just like in the Ramanujan conjectures. And of course, it is the Ramanujan conjectures that assert that certain graphs constructed in a certain way are Ramanujan. And this picture, when I first saw it, explains everything that was in my head. I'd never seen this picture, but it's what I always thought a Ramanujan graph. So Lubotsky, Phillips, and I constructed various Ramanujan graphs. They're explicit, they're very beautiful. And this one is corresponding to a Cayley graph of PSL2 F29. 29 is a prime, it's a field with 29 elements with 6 generators that are cunningly chosen. And the Jacquet-Langlands correspondence is used at some point to show that this graph is Ramanujan. And this graph has the property that when you start at x, at the beginning, you look like the 6 regular tree. That's this girth. The girth is quite big. But then you come to this log base p. So in this case, p is 6 and n is 12,000 and something. And all of a sudden, you seem to be connecting to everybody, but just exactly what the diameter is another question. This is what it looks like. So at the beginning, the girth is large. And the question is, for this kind of Ramanujan graph, what is the sharp cutoff? And this is the numerical picture that's from a paper of Lubotsky and Perez, who answer this, all but answer this question. And here's the sharp cutoff. So this is the numerical experiment with that graph. It starts at 1 and then it drops sharply to 0 with a very sharp cutoff. This is the L1 and L2 cutoff, which I will get into in a minute. And this is their bound from their paper, which looks very good, but it's got a certain weakness, and I want to overcome that weakness. So Lubotsky and Perez show that if you're a Ramanujan graph, so this is a purely combinatorial statement. The only input is the properties of these eigenvalues being limited in the way I described. Then you have, in fact, sharp cutoff. Remember, they're trying to find if the random feature is true for Ramanujan. So they have 1 plus little over 1 log p to the base n is the cutoff. But they do not get a bounded window. So they have to go a lot further, but log is not a lot, but that's, this log is what this talk is about. I want to get rid of that log. You have to actually take an extra bunch of steps in order to make sure that the total variation gets small. So they do not have a bounded window, and that was remained open. And that's the question I want to address, say, for these graphs. Okay. So now I can state the second theorem that we have. So the second theorem is a purely combinatorial theorem. It doesn't use all the stuff I was talking about before, but it's got the ideas of how you're going to do the rest. So you fix delta. So this now is a secondary parameter, which is fixed, which will be a parameter that's very well behaved in the case of those LPS graphs. You fix the delta, and suppose that the girth of the graph grows like delta. Delta is a small number, a constant, small constant times the same log n to the base p. So this is exactly this feature here, that the girth is quite large. Can't be too large, but these girths are quite large. Then this cutoff, then in their theorem, we can get rid of the log. So we have what you'll see in a minute, which is the correct size, log to the base p of n, plus 2 log epsilon inverse. So if you want to go from 1 to epsilon, you need to take a bounded number of steps further. And there's a price you pay, an extra bounded number of steps, depending on this delta, which I'm thinking of as fixed. This is incorrect. Delta is 2/3 for the Ramanujan graph, but that's not going to change anything here. So in particular, this answers the question, as to whether the LPS graphs have bounded window cutoff for the non-backtracking walk, and the answer is yes, and this is this theorem 2 resolves that. Now let me say how we attack this, and this is completely standard in this theory. The total variation was an L1 norm by Cauchy-Schwarz. You can bound the L1 norm by the L2 norm. You can see if it's effective, and in this case, and quite remarkably, for the simple random walk, that's a bit of a problem. But for this non-backtracking walk, this works perfectly if you can understand the variances. And many of us are very much involved in variances in these kind of number theory problems, and this is exactly what's emerging here. So I've normalized here by that important number n, and then I take the L2 norm rather than the L1 norm summed over all y. And then if you just use the spectral expansion, and that's why how we're going to get the eigenvalues into this, you find that this variance, I'll call it, is the sum over some polynomial. It's a polynomial that I would not have written down, but it's the polynomial that corresponds exactly to the non-backtracking random walk. It's a specific polynomial that, in theta. And you need to compute the L2 norm summed over n, and the starting point is also in the answer here, phi j x squared. If I sum over x, this will disappear because phi j x squared, and if x is homogeneous, that's this discussion here, then this is 1 over n. So this looks very much like the beginning. In fact, it is a kind of sum that we discussed in theorem 1. Once we translate all the way back to gamma naught n. There's a very important polynomial. It's the variance polynomial, which is this polynomial in terms of Chebyshev polynomials of the first and second kind. So the Chebyshev polynomial of the first kind is cos t theta, and these are polynomials in cos theta of degree t, and the Chebyshev polynomial of the second kind is sine t plus 1 theta over sine theta. And this polynomial is the critical one to understand everything about the variance. And if you put in the bounds, so if you bound, the polynomial of the first kind is uniformly bounded, and then that's very friendly to you, that term. But this term has actually got a t in it at the origin, and that's the same origin at which the Plancherel measure vanishes. That's what we're going to be using. So at the origin, this is size t, and that puts an extra t squared, and that's the extra log they have in their analysis, which we're trying to get rid of. So it's all in this variance, and the point here is now we can see clearly how it's connected to our starting. So there's something different, but very closely connected. We are averaging over the eigenvalues of this graph. So this graph's not necessarily coming from number theory, but it will in a second. And we're asking whether that average converges to the Plancherel measure, but the polynomial we're putting in here has a degree which is growing. So we're asking for a flexibility in convergence to Plancherel measure where we allow the polynomial to have a certain degree.
Peter.
Yeah. Hello.
Show me your Chebyshev polynomial. Tn theta.
Thank you. Yeah, there's a misprint. That should be TT. Thank you. Yeah, this man is always sharp. The sharpest tool in the shed.
All right.
All right, thank you. If you were able to say that this average with t at the size of log n to the base p, exactly that cutoff, this is exactly where we're trying to establish this, we would get, and if we can put we don't have to worry about anything but the degree, we would get this, and then we could compute this because it's just an integral, and you'll get that actually the variance is nothing but 1 over n in this range, which is an absolutely beautiful answer, and actually one that you can explain in terms of balls and boxes quite nicely. So if this were true, you would get this bound of log n to the base p plus 2 log 1 over epsilon, which is the bounded window cutoff with the optimal, this is completely optimal, I'm sure, and the real truth about the non-backtracking walk on a Ramanujan graph. Now, unfortunately, we don't know this. I don't know how to prove this, other than if I put a girth assumption, I can make an approximation to this. But for all other graphs, if I use the number theory and convert it back, at least to graphs which come back to gamma naught n, where you got this bound. So this is, I'll stop with this because I think I'm supposed to stop at about 9 50. So let me state the theorem. So if XQ is a Ramanujan graph corresponding to modular forms of weight 2 and level Q, so there are many very interesting graphs. The actual homogeneous graphs, the LPS graphs, are not, they actually live on the full congruent subgroup, gamma Q, not gamma naught Q. So these graphs were constructed by Brunt first. They called them Brunt matrix graphs from the theory of theta functions. Ihara constructed these graphs in a paper of his that deserves more attention. These are also the graphs that algebraists love. They are Ramanujan graphs. They've been used for hash functions by Kristen Lauder and people like that. These are supersingular isogeny graphs of the field with Q squared elements, where you look at P isogenies. So Q is the Q and the P is our P in our discussion. And you make a graph by connecting the supersingular primes, the supersingular elliptic curves, which are P isogenous. And you get a connected Ramanujan graph, and it's expressible in terms of these Brunt matrices as well. So for all those graphs, one can prove, thanks to theorem 1, that you have sharp cutoff with this behavior. So you get exactly what you want. I have one caveat there, is in order to get something, there's an X here. So I have to, in these problem, and we haven't sorted this out yet. I would like to have max over X, but right now we'll take a random starting point. So if I average over X, then it's a purely spectral statement and translates to convergence to Plancherel measure without having to worry about this. But in the large girth, we can allow X and still get it. So we obtain this, and this, of course, uses Jacquet-Langland's correspondence to get into the position. So this comes from a quaternion algebra, the graph, and to get to this point, and actually you get the full, beautiful answer for the variance, thanks to the fact that we were able to not necessarily double. You didn't have to double the range in the main theorem. Is corollary 2. We must be able to take C1 plus epsilon, just 1 or slightly bigger than 1. But as I was saying, if you want to go from below 1 to above 1, you may as well try go hit 2, and that's what this method buys you, of removal of weights. And you can't do that by just estimating the class numbers. You have to get cancellation, and that's what we do. All right, I'll stop there, and happy birthday, Bala. And I hope you enjoyed my discussion of your paper of the place in number theory of identity of Ramanujan. I would change it to the place in number theory of your sieve method to get zero free.
Thank you.
Thank you, Peter.
I have a number of more slides, but I don't want to. People are, I'm sure, exhausted after a week. And by the way, I apologize. Obviously, I couldn't go to the talks that were, well, I shouldn't say I couldn't. I could get up in the middle of the night. But if I actually, did anyone discuss this paper of yours, Bala?
I think Ravane had a mention of the paper.
Okay. Well, I hope I didn't say the same thing, but I have a paper.
No, he was looking from a different angle.
Yeah. So when I was, I can tell you a further story just to end with this. This proof using Eisenstein series, Henrik will know this. I had a lot of discussions with Selberg about it. I once asked him, this proof using Eisenstein series of the non-vanishing on the line 1, what does it give in terms of zero free region? And he didn't want to answer. He just refused. He kind of froze. And eventually said a very bad zero free. And I was convinced that it doesn't make sense. And by the way, if you look at the treatments in Langland Shahidi, or the works of Shahidi primarily, Jacquet Shahidi, they just treat this as ineffective, and I didn't like that. So I wanted to make it effective, and I was quite happy to see that your method allows you to bootstrap further from an effective bound of a lower bound of 1/t⁴ to the logarithm. And that's very significant, and I think it's completely misunderstood that Rankin-Selberg is in good shape, only because of your method at present. This is something that might change as people understand more cases of functoriality.
Peter?
Yeah, Henrik.
Yeah, if I remember correctly, I think it was in Stanford when Selberg visited you. I was there too, and somewhere chatting about the prime number theorem proved by Eisenstein series. And I don't know exactly what he said, but I remember the conversation, and he was, so to speak, optimistic about, this kind of.
He actually, and you can find this on, if you go to the Institute website and look under the side, you'll see Selberg, and there are many things that were found in his office after he passed away that are posted there. And in particular, a series of lectures, one of which he gave at Stanford, one he gave in Zurich, on this elementary proof of the prime, on this proof of the prime number theorem by formulating it in a very beautiful way in terms of double coset sums in a discrete subgroup of SL2R, which need not be SL2Z. So you get a statement that you prove for an arbitrary group. When you specialize it to SL2Z, you get the prime number theorem elementarily. You'll find that lecture, but the details are not so complete. In my write-up of my paper is called Non-Vanishing on the Line 1, and I discuss this in some depth, especially in higher rank and Langdon Shahidi. In my discussion, I repeat in a somewhat different language his argument. It's quite beautiful. There's a statement there which is a deformation of the prime number theorem. It shows that there should be an elementary proof, ergodic theory proof. And by the way, recently Richter and Bergelsen gave an ergodic theoretic proof of the prime number theorem. Elementary proof using Chebyshev and ergodic theory. I don't know if you know that, Henrik.
No, I did not. I still have to catch up with you.
That's not me.
But they gave a lecture just a mile away from your house about this a few months ago.
Yeah, well, that's in this world, you may as well be next door. I don't see my neighbor.
By the way, Peter, what I meant by Chebyshev polynomial, the argument should be cosine theta, not theta.
Yeah. Okay, that goes without saying. I can't put that. Yeah. Okay, thank you. I thought you meant the N. Okay.
No.
Good. Any other questions, comments? Okay, so if not, thank you very much, Peter.
Thank you.
And I guess we have a 1 hour break now, if I'm not mistaken, until Ken Arnold's lecture.
ZF, is it your garden behind you?
That is my garden behind me, that's right.
Wow.
That is my garden. It's spring now.
Yeah. No, you are kidding. Is it really true?
No, it is my garden. It's spring. It's like 20 degrees outside. Almost as hot as Chennai, I imagine.
Thank you, Professor Rudnick, for chairing the session. And let us also thank all the speakers of this session.
Yeah, thank you.
And we will meet in an hour.